Friction drains energy from motion, turning speed into warmth and warmth into stillness. Light spreads out and fades, losing its brilliance as distance dilutes it into the darkness. Stars burn their fuel and die. Winds calm. Waves flatten. Everything known seems to surrender its energy to time. Yet gravity endures. It pulls. It binds. It holds galaxies together for billions of years with no sign of fatigue. It reaches across the cosmos, undiminished, shaping the very architecture of the universe, while never appearing to grow tired or weak. The same pull that guided the first stars still guides the paths of planets today. There is no decay, no friction, no fading of its strength through the ages. If one watches the dance of galaxies through deep space, spirals turning like slow whirlpools in a cosmic sea, one finds that gravity remains the unseen conductor. Its influence stretches over hundreds of thousands of light years, and yet there is no visible source of exhaustion. Each orbit continues as though gravity were new, as though it had never done any work at all. This persistence defies the intuition that every process should lose energy. In the realm of human experience, no motion lasts forever. A spinning top wobbles and falls. A pendulum slows as air and friction rob it of momentum. Even the orbit of a satellite must be corrected as atmospheric drag pulls it down. But on cosmic scales, the planets of our solar system circle the sun endlessly. The moon continues its silent journey around Earth, as it has for billions of years. Nothing seems to drain gravity's strength. It would be natural to think that such an enduring power must require infinite energy. But this cannot be. Energy is always accounted for, conserved, transformed from one form to another. Where does gravity's energy come from, and why does it never run out? If the universe truly obeys the laws of thermodynamics, where every process tends toward disorder, why has gravity not succumbed to that same fate? The stars may die, the light may fade, yet the structure of the universe remains bound together by this force that never tires. Some might say gravity is simply too weak to lose energy, but that is not the truth. Weakness alone does not explain immortality. The faint tug between two pebbles in a field may seem negligible, but scaled across the mass of a planet, that same law pulls oceans, bends mountains, and binds the very core of worlds. Even the most delicate gravitational pull accumulates across time and distance until it becomes the framework of existence. Weakness cannot explain endurance. There must be something fundamentally different about gravity. It is not like the other forces. The electromagnetic force can radiate away energy as light or heat. The strong and weak nuclear forces act within atoms and decay over time, their influence confined to subatomic scales. But gravity stretches infinitely and yet never seems to lose its grip. If energy cannot be destroyed, then perhaps gravity does not use energy in the same way. Perhaps it does not consume or expend it. Imagine dropping a stone. It falls to the ground because of gravity, and when it hits, it makes a sound, and that sound carries energy. One might think gravity did work in pulling it down, yet what really happened is subtler. The stone followed a path set by the curvature of space itself. Gravity did not pull in the sense of a hand tugging a rope. The stone merely moved along the path that space told it to follow. The energy came not from gravity itself, but from the configuration of mass and geometry. The stone's motion was an exchange of potential and kinetic energy, not a drain on gravity's strength. This realization opens a deeper mystery. If gravity never runs out, could it be that it never had energy in the first place? Or that its energy exists in a form that cannot dissipate, a kind of eternal bookkeeping within the fabric of reality? Every other force acts upon things. Gravity acts upon the stage itself. It changes what straight lines mean, what direction means, what time means. And so, while it shapes everything, it does not spend itself. Consider how light behaves when it climbs away from a star. Its frequency shifts, its color reddens. Energy is lost from the light, but where does it go? It goes into the gravitational field, subtly altering the geometry of space-time. Yet that geometry does not appear to tire. It bends, it flexes, and it restores itself like a perfect elastic medium that never heats up, never wears down. The universe seems to allow gravity to reshape it indefinitely without friction. This is where intuition begins to fail. In human experience, every action has a cost. Push against something and you feel resistance. Move through air and drag slows you down. Even the smallest electric current meets resistance in a wire, releasing heat. But gravity meets no resistance. The Earth orbits the Sun as it did billions of years ago. No cosmic drag slows it. No hidden friction saps the motion. Space does not resist being curved. Time does not protest being stretched. What kind of phenomenon can act without expending energy, move without motion, and influence without interaction? Gravity may not be a force at all, at least not in the usual sense. It may be a manifestation of geometry itself, the shape of space-time telling matter how to move, and matter telling space-time how to curve. If so, the endurance of gravity is no longer a miracle of energy, but a property of structure. Geometry does not wear out. A triangle drawn perfectly on a sheet does not fade with time. It is an arrangement, not a fuel. And yet, even this comparison fails to capture gravity's reach. Geometry on a page is static. Gravity's geometry is alive, dynamic, shifting as stars move and galaxies evolve. Somehow, the universe continually updates this geometry everywhere, instantly and without loss. It is as though reality has found a way to compute itself, without ever overheating. If this is true, then gravity's persistence is not an exception to the laws of physics, but their deepest expression. The cosmos does not need to feed gravity energy, because gravity is not something that consumes or releases it. It is the bookkeeping of how energy itself shapes the stage upon which everything unfolds. This is why galaxies can whirl and collide for billions of years without gravity running out. It is why black holes can merge and the resulting space-time remains stable. Gravity does not flow through space like a fluid that can be lost. It is the architecture itself. To understand why it never tires, one must first understand what it truly is. The idea that gravity is eternal is not mere poetry. It is a profound clue to the nature of the universe. It hints that what we perceive as forces may be reflections of deeper symmetries, and that energy loss, friction, and dissipation belong only to the realm of matter and radiation. Gravity may belong to the fabric beneath, the substrate that does not wear down because it is not made of moving parts. It is the stillness from which motion arises. To uncover this, one must step back from the familiar notion of forces and begin to see the world not as particles being pushed and pulled, but as geometry itself evolving. What we call gravity may be nothing more than the natural shape of reality. And if that shape cannot decay, then perhaps energy is not what sustains it. Perhaps eternity is written into its equations. The story of gravity, then, begins not with motion, but with form. It begins not with a pull, but with a curve. It begins not with energy, but with the way space and time themselves are woven. To understand why gravity never loses energy, we must first understand that it might never have needed any to begin with. Gravity endures, but endurance without explanation is only mystery. To uncover the secret of its tirelessness, we must abandon the language of force and begin to see motion and attraction in a new way. For centuries, people imagined invisible threads pulling objects toward one another. Newton gave this vision mathematical form, showing that every mass in the universe attracts every other with a strength that diminishes with distance. His equations described the fall of an apple and the path of the moon with the same simple law. Yet even Newton could not tell what gravity was. He could only describe how it behaved. The pull acted instantaneously across the void, as though space itself were only a stage upon which invisible hands reached out. The genius of Newton lay in precision. He could calculate how the planets moved and how tides rose, but he confessed ignorance of the cause behind the attraction. He famously said he framed no hypothesis. The universe seemed to obey his equations perfectly, and for 200 years they guided every ship, every planet, and every scientific mind that sought to measure the heavens. But hidden within that success was a quiet unease. If gravity truly pulled across empty space, What medium carried that pull? How could one mass know about another separated by millions of kilometers? The mechanism was invisible. By the 19th century, physics had learned to see the world as fields filling space. Electricity and magnetism were no longer mysterious attractions between distant objects, but the behavior of continuous fields, patterns of energy spreading through the ether. When James Clerk Maxwell united these ideas into the equations of electromagnetism, light itself became understood as a ripple in that field. Waves replaced pulls. Motion replaced mystery. It was only natural to imagine that gravity, too, might be a kind of field spreading through a medium. But when attempts were made to describe it so, something was always missing. The missing piece came with Einstein. He began with a simple thought. What if gravity and acceleration were indistinguishable? A person in a sealed box could not tell whether the force pressing them to the floor came from the box resting on a planet or from the box accelerating through space. That insight grew into the equivalence principle, the seed of general relativity. The picture of invisible forces was replaced with a deeper vision. Gravity was not a force pulling across space, it was space itself being curved. In this new understanding, matter tells spacetime how to curve, and curved spacetime tells matter how to move. Objects in free fall are not being pulled. They are following the straightest possible paths through a curved geometry, paths called geodesics. The apple falls to Earth, not because an unseen hand drags it downward, but because the geometry of spacetime near Earth bends in such a way that the apple's straight path leads to the ground. The moon orbits, not because it is held by an invisible string, but because its straight path loops endlessly within the sun's curved geometry. Once seen this way, gravity's endurance becomes less strange. Geometry does not tire. The Earth does not lose energy to some hidden friction in the void because there is nothing to rub against. It is simply moving freely through the shape of spacetime. The apparent pull is an illusion born of curved geometry. Gravity is not doing work in the usual sense. It is the framework within which energy exchanges occur, not one of the actors spending or losing it. Yet this understanding came with a price. If gravity is geometry, then energy itself becomes a subtle idea. In flat space, one can define energy cleanly. In a curved, dynamic universe, global energy conservation no longer holds in the same way. Energy can appear to stretch or redshift as the fabric of spacetime expands. The universe itself can grow, and the total energy budget may change in ways that are not violations, but reflections of evolving geometry. This realization shattered the old idea that energy must always be conserved everywhere and at all times. The universe became more like a living structure than a clockwork machine. Einstein's equations did more than redefine gravity, they redefined reality. They revealed that what we call space and time are not separate, empty containers, but intertwined and malleable. Every mass and every photon bends that fabric, and the bending in turn dictates how everything moves. In this web, energy is local, defined only in small regions where spacetime can be treated as almost flat. Globally, the concept of energy becomes ill-defined because the stage itself is shifting. But if energy cannot be globally conserved, how can we still speak of gravity's endurance? The answer lies in understanding that geometry is not subject to the same bookkeeping as motion. When the universe expands, the wavelengths of light stretch, their energy decreases, but nothing has been lost. The total pattern of spacetime has simply changed. Gravity's apparent unending strength comes from its nature as that pattern. It cannot dissipate because it is not a substance. This vision invites awe. Imagine the cosmos not as a collection of objects floating in emptiness, but as a vast, curved continuum, where hills and valleys of geometry guide the flow of stars and light. In this continuum, there is no need for a force to pull or push. Everything moves along the lines carved by spacetime's curvature. A planet in orbit is not fighting resistance, not burning fuel. It is falling forever along a path that repeats itself. a path requiring no expenditure, no renewal of strength. In such a universe, gravity is not a tireless worker, but a silent architect. Its power is not in motion, but in form. The planets move because of the shape of space-time, not because gravity is pushing them forward. This is why it cannot fade. A shape cannot grow weary. A curve cannot exhaust itself. The elegance of this idea hides its strangeness. To say that gravity is not a force is to overturn centuries of intuition. It means that what feels like a pull toward the Earth is actually the natural path through a bent geometry. It means that when you drop a stone, it is the ground that rushes up to meet it, each following their natural trajectory through curved space-time. It means that the universe's endurance is not powered, but shaped. Still, this view raises another question. If gravity is geometry, then what happens when that geometry changes rapidly, as in the collision of two black holes? The fabric of space-time ripples, and those ripples propagate outward as gravitational waves. These waves carry energy, and their detection proves that gravity can, in a sense, radiate. Does this mean gravity finally dissipates? Or does it mean that even its radiation is part of the same perfect geometry, conserving something deeper than ordinary energy? The next part of this story turns to that question, where the sound of space-time itself reveals how gravity can carry energy through the cosmos without ever depleting its essence. The idea that space itself can ripple seemed once impossible, yet nature has confirmed it. When two black holes spiral together, they do not merely disturb the matter around them, for there is no matter left to disturb. They shake the very geometry of space-time. These ripples, known as gravitational waves, travel outward at the speed of light. They carry information about the event that created them, the masses involved, the shape of the final merger. In 2015, the Laser Interferometer Gravitational Wave Observatory detected these waves for the first time, capturing the faint stretching and squeezing of space that occurred when two black holes, billions of light years away, collided. It was as though the universe itself had spoken, and we had finally learned to listen. These waves are energy in motion, yet they do not represent the exhaustion of gravity. When a stone is dropped into a pond, ripples spread outward and the surface slowly becomes calm again. The energy of the ripples eventually dissipates as heat in the water. But when black holes merge, the waves of space-time travel across the cosmos without resistance. There is no medium to heat, no friction to slow them, no viscosity to absorb their motion. They pass through planets, stars, and galaxies almost untouched, their presence measurable only by instruments of extreme precision. Even after crossing billions of light years, the amplitude of such waves changes only because of the expansion of space itself, not because of any loss to friction. This is why gravity's waves are said to be dissipationless. They carry energy, but the medium that carries them cannot tire, because it is not a material. Space-time does not heat up. It does not scatter. It is geometry in motion, the purest form of energy transport that nature allows. The electromagnetic field, though elegant, can be absorbed and re-emitted, scattered and polarized. Light can be trapped or dimmed by matter. But gravitational waves move through the universe as if through emptiness beyond emptiness, unimpeded, eternal in their journey. This quality tells us something profound. Gravity is not a field in the usual sense. It is not something laid atop space-time. It is space-time. Its vibrations are not disturbances of a background. They are the background changing shape. When one speaks of energy radiating away as gravitational waves, one is really describing the redistribution of curvature, the smoothing out of geometry's own fabric. The energy does not vanish. It simply takes a new form, a new configuration. Even so, there is something delicate about this energy. Because gravity interacts so weakly, even the most violent cosmic events release only faint signals detectable here on Earth. A black hole merger can release more energy in a second than all the stars in the observable universe combined. Yet by the time its waves reach us, the distortion of space they produce is smaller than the width of a proton. This near invisibility is not weakness in the ordinary sense. It is efficiency. The universe wastes nothing in transmitting these waves. If gravity can transmit energy without losing it internally, it behaves like a perfect superconductor. In an ordinary conductor, electric current faces resistance. Some energy is lost as heat. In a superconductor, current flows without resistance, potentially forever. The energy does not dissipate because the material's quantum state forbids it. Similarly, gravity appears to exist in a state of perfect coherence. It can change shape, send waves, merge and expand, but it never decays into randomness. Its geometry preserves information and structure with infinite fidelity. This might be why the universe can continue to evolve without its gravitational framework collapsing. Gravity can transmit the drama of cosmic events without consuming itself in the process. When black holes merge, the resulting spacetime is not weaker. The merged black hole's gravity is as pure and precise as ever. It is as though the universe itself refreshes its geometry seamlessly, like a perfect system updating its own equations in real time. There is a mathematical reason for this perfection. The equations of general relativity are conservative in a way that differs from other field theories. They describe how curvature and energy momentum relate, but they do not allow internal dissipation within spacetime. Every motion, every ripple, is accounted for in geometry's structure. The curvature evolves deterministically, guided by Einstein's equations, without hidden loss. This is what makes the universe stable. If gravity were dissipative, if spacetime could lose energy to some unseen reservoir, galaxies would have long ago unraveled, planets would have spiraled into stars, and the cosmic web itself would have dissolved. Instead, the universe persists. Its vast structures continue to move as if bound by an invisible promise of endurance. Gravity's dissipationless nature is not merely a property, it is a necessity. Without it, the cosmos would be transient, fleeting, chaotic. With it, we are given continuity, stability, and order. The orbits of planets, the shapes of galaxies, the coherence of the universe itself, all depend on this eternal geometry. This realization also blurs the distinction between energy and form. If geometry can carry energy as curvature, and if curvature cannot dissipate, then perhaps energy itself is geometry in motion. The universe may not truly separate matter and space, energy and form. They are expressions of one continuous reality. In this view, gravity is not a power acting upon things. It is the language through which the universe maintains its own coherence. As gravitational waves pass silently through us, bending space by a fraction of a fraction, we experience a reminder of this unity. The waves do not tire. They do not fade into noise. They continue their journey across time, tracing the living memory of events that occurred before life on Earth began. They are whispers of geometry, carrying the record of creation without ever diminishing it. The dissipationless flow of gravity thus hints at something deeper than endurance. It suggests that the universe operates according to principles more fundamental than the conservation of energy. Perhaps there exists a deeper conservation law, one of information or symmetry, that ensures the total pattern of spacetime remains balanced. Every curvature, every wave, every expansion fits into that balance. Gravity, then, is the harmony of the cosmos. It is the pattern that never breaks, the motion that requires no engine, the song that needs no singer. It speaks through the silent rhythm of spacetime itself, carrying the memory of creation forward without fatigue. And to grasp this harmony fully, one must see beyond fields and forces into the thermodynamic and quantum nature of spacetime itself, where temperature, entropy, and geometry begin to merge into a single idea. The story of gravity begins with wonder. For centuries, humans looked upward and saw a sky of motion. The moon gliding through its phases, the planets wandering against the background of fixed stars, the endless rhythm of sunrise and sunset. All of it hinted at a hidden order. To the ancients, these motions were the work of divine harmony. To Isaac Newton, they were the result of a single, simple rule. Every object in the universe attracts every other with a force that grows weaker as distance increases. This rule united the heavens and the earth. The apple falling from a tree and the moon circling the planet followed the same invisible command. Newton's law of universal gravitation was one of the greatest triumphs of human thought. It described the entire cosmos with an equation so simple that it could be written in a few lines. It gave sailors the means to navigate, astronomers the tools to predict eclipses, and scientists the language to measure the universe. The concept of force became the foundation of physics. A force was a push or a pull that caused motion, and gravity was the most majestic of them all. It seemed eternal, universal, and mechanical. But hidden within this success was a mystery that Newton himself could not resolve. How could one object pull on another across the emptiness of space? When the Earth draws an apple downward, what carries that pull? When the Sun holds the planets in orbit, what medium transmits that grip? Newton admitted he did not know. He could only describe what happened, not why. In his time, this was enough. The universe could be imagined as a grand machine built of forces and masses, gears and motions. It was elegant, predictable, and eternal, or so it seemed. For 2 centuries, Newton's universe ruled. Astronomers used his equations to chart the orbits of planets and comets with astonishing accuracy. Yet small irregularities began to appear. Mercury's orbit, for example, did not match Newton's predictions perfectly. The deviation was tiny, but it persisted. Some believed an unseen planet might be tugging on Mercury. Others wondered if Newton's law itself was incomplete. The puzzle remained unsolved until the early 20th century, when a new vision of gravity emerged. One that would change not only physics, but the meaning of space and time themselves. Albert Einstein began from a simple question. What does it really mean to feel a force? When you stand on the ground, you feel the weight of your body pressing against your feet. But if the floor beneath you vanished and you began to fall, that feeling would disappear. You would be weightless, yet gravity would still be acting on you. It seemed strange that something so strong could be felt one moment and vanish the next. This led Einstein to a profound realization. Gravity and acceleration might be the same thing. Imagine a sealed elevator floating in deep space. If the elevator begins to accelerate upward, you will feel pressed to the floor, just as if you were standing on Earth. There is no experiment you can perform inside the elevator to tell whether the pressure you feel is due to gravity or acceleration. This is the equivalence principle, the cornerstone of Einstein's theory of general relativity. It says that gravity is not a separate force at all, but an effect of motion and geometry. From this insight came a revolution. Einstein proposed that space and time are not separate, fixed backgrounds where events occur. They are a single, dynamic entity called space-time. Matter and energy do not merely move through this fabric, they shape it. Massive objects like stars and planets curve space-time around them, and what we experience as gravity is simply the motion of objects following the straightest possible paths through that curved geometry. These paths are called geodesics. The apple does not fall because the Earth pulls it downward. It falls because space-time around the Earth is curved, and the apple is following the natural slope of that curvature. The same applies to the Moon's orbit. It is not held by an invisible tether, but glides freely along a curved trajectory shaped by the Sun and Earth together. There is no force in the traditional sense, only geometry guiding motion. This view was radical. For the first time, gravity was not a fundamental interaction like magnetism or the nuclear forces. It was a manifestation of the shape of reality itself. The stage upon which the universe played was not flat, but flexible, capable of bending and stretching. Space could expand, time could slow, and the geometry of the cosmos could evolve. The Sun did not emit a gravitational pull, it sculpted space-time. The Earth and other planets simply moved within that sculpture. To understand how revolutionary this idea was, one must imagine what it replaced. Newton's universe was a grand clockwork where forces acted across empty space. Einstein's universe was a living continuum where geometry replaced force and curvature replaced attraction. Gravity was no longer a thing that acted on matter, but a rule that told matter how to move. And matter, in turn, told space-time how to curve. In this picture, there is no expenditure of energy when objects move under gravity. A planet orbiting a star does not need a constant input of energy to maintain its path. It simply follows the geometry of space-time, which costs nothing to sustain. There is no friction, no resistance, no hidden drain. The planets glide effortlessly, not because gravity is infinitely strong, but because it is not a force at all. This realization also explains why gravity seems eternal. Geometry does not tire. A mountain does not lose its shape because a river flows around it. The curvature of space-time does not fade because a planet orbits within it. As long as the masses remain, the geometry remains. When masses move or merge, space-time adjusts smoothly, redistributing curvature without loss. The fabric of the universe behaves like a perfect medium, not because it is made of a substance, but because it is the framework that defines all substances. Einstein's vision reshaped not only physics but philosophy. If space and time could curve, then they could also evolve. The universe itself could expand or contract. The boundary between matter and geometry blurred. Space was no longer emptiness, it was a participant in the cosmic drama. Time was no longer a universal rhythm, it flowed differently depending on gravity's influence. To test this idea, Einstein predicted that light passing near a massive object would bend. In 1919, during a solar eclipse, astronomers measured starlight deflected by the sun exactly as his theory predicted. The triumph was instant and complete. Newton's invisible force was gone, replaced by a geometry that curved both space and light. The universe was not a machine, but a structure of relationships, a web of curvature and motion bound by mathematical elegance. This change of view also redefined the meaning of energy. In Newton's world, potential energy and kinetic energy were easily defined in terms of forces and motion. In Einstein's world, energy became entwined with space-time itself. A mass resting in a gravitational field has energy not because it is being pulled, but because of its position in the curvature of space-time. When it falls, it simply trades one form of geometry for another. Nothing is lost. Nothing is consumed. To call gravity a force, then, is to misinterpret what it truly is. It is the expression of how energy and matter shape the very stage upon which they exist. It is the curvature of existence, not a current flowing through it. This is why it does not fade. Forces dissipate. Geometry endures. The planets will continue to orbit their stars long after their light has dimmed, not because gravity has infinite strength, but because it is written into the language of the universe itself. And yet, even in this elegant vision, mysteries remain. If gravity is geometry, can we speak meaningfully of gravitational energy at all? Can geometry store or release energy the way a field does? When galaxies collide and space-time ripples, where does that energy reside? These questions lead us to the paradox at the heart of general relativity, a paradox that reveals why energy itself may be an illusion when viewed on the scale of the universe. In the realm of general relativity, energy becomes a subtle and elusive idea. In the physics of everyday life, energy is a clear and familiar concept. A ball held above the ground has potential energy, and when released, that energy turns into motion. Friction, air resistance, and heat can take some of that energy away, but it never vanishes. It simply changes form. In the mechanical world described by Newton, this law of conservation is absolute. Energy cannot be created or destroyed. It can only move or transform. Yet when the stage of the universe itself becomes dynamic, this simple rule begins to blur. Einstein's equations describe how matter and energy tell spacetime how to curve, and how curvature tells matter and light how to move. These equations are local. They work perfectly in any small region of the universe. If you look at a patch of spacetime, no larger than a laboratory or a solar system, you can describe the flow of energy precisely. Energy moves from place to place according to exact mathematical laws. But if you try to define the total energy of the entire universe, the concept slips through your fingers. There is no single number that captures the total gravitational energy of a curved and expanding cosmos. This is not a failure of the theory, but a reflection of its depth. Energy conservation depends on time being uniform, on the universe having a fixed rhythm. In a curved, evolving spacetime, time itself stretches and bends. The universe expands, galaxies drift apart, and light from distant stars is stretched into longer wavelengths, losing energy as it travels. But that lost energy does not go anywhere. It simply ceases to be defined in the same way, because the very geometry that measured it has changed. To understand this, imagine a wave traveling across a calm sea. Its height and speed can be measured easily. But if the sea itself begins to expand, the meaning of the wave's energy changes. The wave does not give its energy to the sea in any ordinary sense. Instead, the scale of measurement changes beneath it. The same happens in the universe. As space expands, light's wavelength increases and its energy decreases. Yet nothing in the universe absorbs that energy. The total structure of space-time has simply reshaped itself. The energy has not vanished. The meaning of energy has evolved. In Newton's view, space and time were fixed backgrounds where energy was measured. In Einstein's view, the background itself is active. The curvature of space-time can change in ways that make energy conservation a local rule, but not a global one. Physicists express this by saying that energy momentum is conserved locally, but not globally. In small regions, the equations hold with perfect precision. Over the entire universe, the concept of total energy becomes undefined. This leads to a strange and beautiful conclusion. Gravity does not lose energy because gravity does not possess energy in the usual sense. It is the geometry of reality, not a separate field superimposed on it. When we say that a falling stone gains energy, we mean that its motion changes relative to the curved geometry of spacetime. The energy is a relationship, not a substance. Gravity does not give or take energy. It provides the stage upon which such exchanges can occur. This also explains why gravity can appear to radiate energy through gravitational waves without depleting itself. When two black holes spiral together, they distort space-time, sending out ripples that carry measurable energy. Yet this energy is not drawn from a reservoir within gravity itself. It is drawn from the motion and mass of the black holes. The geometry changes, but the total structure of space-time remains consistent. Gravity is not exhausted by the waves it transmits. The field does not fade, because it is not a field in the ordinary sense. It is the metric that defines all fields. Physicists have long sought to define gravitational energy more precisely, but every attempt leads back to the same difficulty. Energy can only be defined relative to a fixed background, and gravity provides no such background. The universe has no external reference frame. Space and time themselves are the framework. There is nowhere for gravitational energy to flow, because everything that exists is contained within the geometry it defines. Some solutions exist in special cases. In isolated systems, like a single star surrounded by empty space, one can define an approximate notion of gravitational energy by comparing it to flat space far away. This leads to concepts like the ADM mass, a mathematical measure of the total energy content of a system as seen from infinity. But for the universe as a whole, there is no infinity beyond it to make such a comparison. The cosmos is self-contained. Its energy is not stored anywhere because there is no outside to store it in. This realization unsettled many early physicists. It seemed to challenge the very idea of conservation that lay at the heart of classical science. But Einstein's universe does not break conservation, it transcends it. The geometry of spacetime encodes the relationships that make conservation meaningful. Where curvature changes, local energy flows adjust accordingly, maintaining balance within their own regions. On the cosmic scale, there is no contradiction, only a deeper harmony that escapes simple arithmetic. One can think of it this way. In a flat, static world, energy is a countable quantity. In a curved, living universe, energy becomes a language of change. It no longer measures content but connection. The curvature of space-time records how matter moves, and matter records how curvature evolves. The two form a self-consistent whole that neither gains nor loses energy in the traditional sense. Gravity's endurance is built into this unity. It cannot dissipate because there is no external arena into which it could dissipate. Even when the universe expands, even when galaxies drift apart and the night sky grows dimmer with age, gravity remains undiminished. The curvature that defines it stretches, but the rule itself never fades. It is not a current that must be sustained. It is the equation that sustains everything else. In this light, the apparent paradox of energy and general relativity becomes not a problem, but a revelation. It tells us that gravity is not a force in the sense of something expending effort. It is the timeless shape of reality's flow. The geometry of spacetime evolves according to its own logic, always consistent, always balanced, never exhausted. The universe does not run down like a machine losing power. It unfolds like a geometry continuing its pattern. If the cosmos is a living shape rather than a mechanism, then gravity's persistence is no longer a mystery. It endures not because it resists entropy, but because it is the structure through which entropy itself is measured. It is the stillness beneath all change, the equilibrium that defines motion without partaking in it. And yet, this quiet endurance has a voice. When massive bodies collide, when stars explode, when black holes merge, the geometry itself rings like a bell. The ripples that emerge, the gravitational waves that stretch across the cosmos, are the sound of spacetime in motion. They carry energy, yes, but they do not weaken the universe. They are the music of an instrument that never wears out, the vibration of a fabric that has no friction. To understand how this can be true, we must listen closely to those waves. They reveal that space-time is not silent but resonant, and that even in its most violent moments, gravity remains lossless. The next part of this journey enters that realm, where the universe sings through geometry, and the sound itself proves that gravity does not tire. In the silent depths of space, where light from the nearest star may take thousands of years to arrive, the universe hums with waves too faint for any human sense to feel. These are not waves of sound or light, but of space-time itself. They ripple outward from cataclysms so vast that their echoes bend the very geometry of existence. When two black holes spiral together, their enormous masses twist the fabric of space-time into motion. As they merge, the distortion spreads outward like ripples from a stone cast into a boundless pond. These ripples are gravitational waves, and they carry with them the story of their origin, the final heartbeat of colliding giants. In 2015, instruments on Earth first detected these faint distortions. Two observatories, one in Louisiana and one in Washington, each used lasers to measure the lengths of enormous tunnels of vacuum with unimaginable precision. When a gravitational wave passed through, it stretched one arm of the tunnel while compressing the other by a distance smaller than a single proton. That minute change, recorded as an almost imperceptible signal, marked the first direct detection of a gravitational wave. It confirmed what Einstein had predicted a century earlier, that gravity can move, oscillate, and travel as a wave of geometry through the cosmos. Yet this discovery deepened the mystery rather than ending it. If gravitational waves carry energy, how can gravity remain eternal and undiminished? When two black holes collide, the energy released as gravitational radiation is immense. In that brief instant, more than the combined luminosity of all the stars in the observable universe. And yet, when the waves have passed, gravity itself is unchanged. The merged black hole's gravitational field is as perfect and tireless as ever. How can a phenomenon lose energy and yet remain whole? The answer lies in the nature of the field itself. Gravitational waves do not move through space as light moves through air or glass. They are the motion of space. When a wave passes, nothing is displaced. The distances themselves are momentarily redefined. The wave carries information about how space-time has been reshaped. It is not a packet of energy traveling through a medium, but a self-propagating change of geometry. There is no friction, because there is nothing external to resist it. In an electromagnetic wave, photons can scatter from atoms and lose energy. The field interacts with matter. It heats, glows, and radiates. But space-time has no atoms to scatter from. There is no lattice beneath it, no particles to absorb its vibrations. The gravitational wave glides through the universe almost perfectly undisturbed. It may pass through entire galaxies, bending them by infinitesimal amounts, and emerge on the other side as strong as when it began. This is dissipationless motion, propagation without loss. The concept of dissipation is familiar in daily life. When a pendulum swings, air resistance and friction in its pivot drain its energy until it stops. When an electric current flows through a wire, some of its energy is lost as heat because electrons collide with atoms. But gravity has no such collisions. It interacts so weakly with matter that even the densest planet is nearly transparent to it. A gravitational wave can pass through a neutron star, one of the densest objects in the universe, without significant alteration. This weakness is not imperfection, but perfection of another kind. It ensures that gravity can transmit information across billions of light years without being blurred or absorbed. To say that gravitational waves carry energy is true, but one must understand that this energy is not extracted from gravity itself. It is the result of motion within space-time, of masses accelerating and redistributing curvature. When two black holes orbit each other, they lose orbital energy in the form of gravitational radiation. The waves carry that energy away, and the orbit shrinks until the black holes collide. Yet the gravitational field as a whole remains pristine. The energy is simply transformed from one geometric configuration into another. This is what makes gravity different from all other known interactions. It is the only phenomenon that can carry energy purely through geometry. There are no mediating particles required for the process to occur, at least not in the classical sense. The fabric of space-time itself undulates, and those undulations move at the speed of light, without resistance. This makes gravity the universe's most perfect communicator. It can transmit signals from the birth of black holes to the edges of time without losing meaning. Physicists often describe this perfection by comparing it to a superconductor. In a superconductor, electric current flows without resistance. The electrons move in perfect coordination, protected by quantum coherence. No heat is generated because the motion does not disturb the underlying structure. In a similar way, space-time supports the flow of curvature without internal loss. Its vibrations are coherent by nature. The universe cannot heat up from gravity's motion because gravity is the framework within which heat and temperature are defined. Even at its most violent moments, gravity remains serene. When a black hole merger sends a burst of waves across the cosmos, the waves themselves do not ruffle the vacuum. They reshape it for an instant, then pass. The region returns to calm without any trace of wear. It is as though space-time were made of a fluid so pure that motion through it leaves no residue. The dissipationless quality of gravity also explains why the universe can endure for billions of years without gravitational decay. Stars orbit galactic centers, galaxies dance in clusters, and clusters weave into cosmic filaments, all held together by gravity's unending embrace. No invisible friction slows this motion. The structures may evolve under their own dynamics, but gravity's role remains consistent and unbroken. It is the conductor, not the performer. This property also means that the information carried by gravitational waves is uniquely pristine. Light can be absorbed, scattered, or redshifted, its message blurred by matter and dust. But a gravitational wave arrives almost exactly as it was when it left its source. It carries with it the fingerprint of the event, the masses, the spins, the merger's rhythm, encoded in the changing curvature of space. It is the purest record the universe can keep. And yet, gravity's losslessness also raises a question. If space-time can carry information without loss, is it perhaps the ultimate information medium? Does the universe store all that has ever happened within its geometry, preserved in subtle patterns of curvature? If so, then gravity's endurance is not only physical, but informational. The universe might remember everything, not as a narrative, but as a texture of space-time itself. In this way, the detection of gravitational waves was more than a technical triumph. It was a philosophical one. It showed that the universe has a way of speaking that never fades. Every motion, every collision, every transformation leaves a trace in space-time structure, carried forever outward in perfect silence. Where all other forms of energy fade and dissipate, gravity endures as an eternal record keeper. To grasp why gravity can behave this way, we must look deeper into the foundations of thermodynamics. The next step of this journey reveals that space-time itself may possess temperature, entropy, and even a kind of internal equilibrium, not in the sense of heat and matter, but in the balance of information and geometry. The dissipationless flow of gravity might arise because the universe, at its most fundamental level, is already at thermodynamic equilibrium. The deeper one looks into the geometry of the universe, the more elusive energy becomes. Gravity, once thought to be a mighty pull, is now revealed as curvature, and this revelation leads to a strange contradiction. If gravity is geometry, how can we speak of gravitational energy at all? Geometry does not radiate heat, it does not glow, it does not dissipate, yet we speak of gravitational waves carrying energy across the cosmos. Somewhere between the elegant mathematics of general relativity and the language of classical physics, the meaning of energy begins to shift. In the familiar world of Newton, energy was a perfect accountant. Every joule that disappeared from one place reappeared in another. The equations balanced, and the universe was a grand ledger of motion and exchange. But Einstein's curved space-time defies such simplicity. The very geometry that defines energy is itself dynamic. When space expands, it stretches the waves of light moving through it, and the light loses energy in the process. Yet that lost energy has no destination. It is not absorbed or transformed. It simply ceases to be measurable in the same way. The expanding universe rewrites its own bookkeeping as it grows. Physicists learn to live with this paradox, but it remains unsettling. Conservation of energy is one of the most sacred laws of nature, and yet in the universe at large it appears to fail. To understand why, one must recall that conservation laws depend on symmetry. When a system behaves the same at every moment in time, energy is conserved. But when time itself is woven into a changing geometry, the rules no longer apply. The universe is not static. It expands, curves, and evolves. Its symmetries are local, not global. Energy can be conserved in small regions, but not across the whole. This means that when light from a distant galaxy arrives redshifted, its loss of energy is not a loss in the traditional sense. The photon has stretched with the universe, and what we call its diminished energy is simply a reflection of a new scale of space-time. The geometry has changed, and with it, the meaning of energy has changed. The universe has no external frame against which to measure itself, so the total energy of the cosmos has no fixed definition. And yet, in certain cases, physicists can speak meaningfully of gravitational energy. Around isolated systems, like stars, planets, or black holes, space-time becomes nearly flat, far from the source. There, energy can be defined relative to the quiet geometry of infinity. This gives rise to concepts like the ADM mass and Bondi energy, mathematical measures that capture how much curvature a system contributes to the cosmos. These quantities are consistent, testable, and measurable through gravitational waves, but they rely on boundaries at infinity, and in an infinite universe, those boundaries may not exist in any physical sense. The paradox deepens when one realizes that gravity seems to both lack and radiate energy at the same time. A merging pair of black holes emits gravitational waves, and those waves can be detected as real energy transfers. Yet the gravitational field itself, the curvature that makes those waves possible, does not weaken in any lasting way. The waves represent changes in geometry, not losses from a reservoir. The field adjusts, redistributes, and continues unchanged in its nature. This quality reveals something profound about general relativity. Unlike any other field theory, it describes a system that is entirely self-contained. There is no background stage on which events unfold. The geometry of space-time is both the actor and the stage. When space-time curves, it is not moving within something else. It is redefining what motion means. In this context, asking where gravitational energy goes is like asking where the surface of a wave goes when the sea becomes calm. The question assumes a separateness that does not exist. And yet this paradox is not merely a philosophical curiosity. It has physical consequences. When cosmologists model the early universe, they find that as space expanded, the energy density of matter and radiation decreased. But the gravitational field, described by the equations of general relativity, evolved in such a way that the total geometry remained consistent. In this sense, gravity acted as a perfect counterbalance, allowing the cosmos to expand without violating the deeper harmony of its equations. The energy of the universe did not vanish. It transformed into curvature, into structure, into the fabric itself. This is why the universe can continue expanding indefinitely without requiring an external source of power. Gravity does not fuel the expansion, nor does it resist it. It defines it. The stretching of space is not an expenditure of energy, but an evolution of geometry. The cosmos is not burning through fuel. It is reshaping itself, guided by the logic of Einstein's equations, which describe change without consumption. One might imagine space-time as a vast, flexible canvas. The presence of matter draws curves upon it, and those curves determine how matter moves. When the matter moves, the curves adjust, always maintaining the balance dictated by the equations. No energy is lost because the universe does not operate on a foundation of transactions. It operates on relationships. The geometry of space-time is a perfect ledger, one that never loses track of its entries, because every curve and every motion are written in the same ink. This is why the concept of gravitational energy, though mathematically difficult, is physically consistent. The universe does not lose energy through gravity, because gravity is not an energy flow. It is a geometric condition that evolves. When we say a system radiates gravitational waves, we are describing the reorganization of curvature, not the depletion of a force. Gravity does not run down. It redistributes itself endlessly in perfect harmony with the motion of matter. If this seems abstract, consider the Earth orbiting the Sun. In Newton's world, the Earth is constantly being pulled by the Sun's force, and if that force were to cease, the planet would fly away. In Einstein's world, there is no pull. The Earth is following the natural curve of space-time created by the Sun's presence. It moves effortlessly, without exchange, without friction. The orbit endures not because energy is being spent, but because no energy is required. In this way, general relativity transforms our understanding of motion and endurance. Energy conservation, so central to all other physics, becomes a local principle, true in small regions, approximate in others, undefined in the whole. The universe's total energy may be zero, perfectly balanced between the positive energy of matter and the negative energy of gravitational curvature. If so, the cosmos could exist forever without needing to draw upon any external source. It is its own equilibrium, self-sustaining, self-defining. This is the heart of the energy paradox in general relativity. Gravity does not lose energy because it does not operate within the same bookkeeping as other forces. It is not a transaction, but a condition. The curvature of space-time neither depletes nor accumulates energy. It expresses the distribution of everything else. When the universe expands, when light redshifts, when stars collapse, all of these changes are reconciled within geometry itself. There is no debt, no imbalance, no fatigue. And so, the endurance of gravity is not the defiance of physics, it is its perfection. The equations of Einstein's theory describe a world where energy is local, motion is free, and geometry itself is the ultimate conservation law. Space-time does not lose energy because it is the reference against which all energy is measured. It is the still foundation beneath all change, the silent accountant of the cosmos. Yet, even this understanding invites a deeper question. If the fabric of space-time can curve, ripple, and expand, then what are those ripples truly made of? What moves when gravity moves? If geometry itself can oscillate, then perhaps the universe possesses a deeper order, a thermodynamic harmony that ensures every motion remains perfectly balanced. To grasp why gravity never dissipates, we must now look at space-time not only as geometry, but as a system in thermal equilibrium, where entropy and temperature govern the very shape of existence. The paradox of energy in general relativity reveals an astonishing truth. Energy itself may not be a fundamental thing, but a description of relationships inside geometry. To explore this further, one must examine the way Einstein's equations handle energy locally, and how those same equations dissolve the meaning of total energy when viewed from the cosmic scale. The mathematics of general relativity is built upon the Einstein field equations, which connect geometry to energy and momentum. They tell us that space-time curvature at any point is proportional to the distribution of mass and energy there. This balance is expressed not through a simple transfer, but through a tensor equation, a rule that ensures that, in any small region of space-time, the flow of energy and momentum is perfectly conserved. Local conservation always holds true. The structure of the equations enforces it, as if the universe itself refuses to lose track of energy within its infinitesimal neighborhoods. But this rule applies only locally. The moment one tries to extend it beyond a small patch of space-time, the entire concept of total energy begins to unravel. The universe is curved, and curvature means that no single notion of time exists everywhere. Without a single, universal time, energy cannot be added up meaningfully across vast distances. What is conserved for one observer may appear to change for another because their measurements of time and distance belong to different geometries. The universe does not offer a single global frame against which to measure its own contents. This is not a failure of physics, but a property of reality. When space-time is curved, there is no consistent way to define an absolute energy reference. Instead, what remains conserved is the geometry itself, the interlocking web of curvature and motion that evolves according to Einstein's equations. In a sense, the geometry takes over the role that conservation laws played in classical physics. The universe no longer needs a fixed total energy to remain balanced. It remains balanced by virtue of its own geometric consistency. To see how this works, imagine the expanding universe. light from distant galaxies stretches as space grows. Its wavelength becomes longer, its energy smaller. From our perspective, it looks as though the universe is losing radiant energy as it expands. But where does that energy go? There is no destination. The redshift does not transfer energy to any medium. It reflects the changing geometry of space-time itself. The expansion alters what we mean by energy, not because the light has been robbed of its strength, but because the yardstick by which we measure its strength has changed. In this picture, the universe is not a system spending energy to expand. It is a geometry evolving under its own equations. The apparent loss of photon energy is not a violation of conservation, but a transformation of definition. As space expands, the relationships between points change, and with them, the way energy is expressed. Gravity does not power or resist this process. It defines it. The field equations link matter, motion, and geometry in a harmony where no external accounting is required. Even in regions of strong curvature, this logic holds. Near a black hole, energy can appear to behave strangely. A particle falling toward the event horizon gains kinetic energy, but to a distant observer, its light becomes infinitely redshifted as it approaches the edge. The observer sees it slow, fade, and freeze at the horizon, its energy apparently vanishing into nothing. Yet for the particle itself, nothing unusual occurs. It continues its descent freely, following the curvature of space-time. The contradiction exists only in comparison, because energy is measured differently in each frame. There is no single truth about energy that applies to both perspectives. This relativity of energy might feel unsettling, yet it hints at a deeper beauty. Gravity unites matter and geometry so completely that no external description is needed. The universe conserves itself by changing shape. It does not require energy to sustain its structure because it is its own structure. When we look at the cosmos and see galaxies receding, stars collapsing, and waves rippling through space-time, we are witnessing transformations of geometry, not transactions of power. This geometric view also explains why the universe can persist for billions of years without running down. In classical systems, motion leads to dissipation. Friction, resistance, and radiation drain energy until equilibrium is reached. But space-time has no external environment with which to share or lose energy. It is a closed system whose geometry evolves in perfect balance. There is no friction in the curvature of reality itself. To understand this balance mathematically, physicists use a quantity called the stress-energy tensor. It describes how energy and momentum are distributed and how they flow through space-time. The Einstein equations ensure that this tensor has zero divergence, a condition that enforces local conservation. It is as though the fabric of space-time keeps perfect records at every point. Yet those records do not add up to a single cosmic account. The universe keeps its balance locally, not globally. In a small region, the rule is exact. What flows in must flow out. In the cosmos as a whole, however, the idea of flowing out loses meaning. There is nowhere outside the universe for energy to go. The cosmos is its own boundary, and geometry ensures its self-consistency. This is why general relativity allows for an expanding universe that does not consume fuel. The equations do not describe a machine that runs, they describe a geometry that evolves. This local conservation also means that gravitational effects are always self-consistent. When energy seems to vanish in one form, it reappears in another within the same region of space-time. The motion of matter generates curvature, and curvature guides matter's motion. The feedback between them is perfect. Nothing is lost. Everything is redefined. In this way, the energy paradox is not a flaw, but a window into a deeper order. Gravity's endurance is not an exception to the laws of physics. It is the ultimate expression of them. The geometry of space-time acts as the universal regulator, ensuring that change and balance coexist. No part of the universe acts alone. Every motion is woven into the whole. If one could step outside the universe and watch it from beyond, one might see that energy, curvature, and motion form a seamless pattern without beginning or end, without loss or gain. But since there is no outside, this vision remains a thought experiment, a reminder that energy itself is a concept born from perspective. Gravity's endurance reveals that the universe may not conserve energy in the way we imagine, but it conserves coherence, form, and information. It cannot tire because it does not move through something else. It is the something else. Thus, when we say that gravity does not lose energy, we are really saying that space-time does not run down. The geometry that governs the cosmos is self-maintaining, self-consistent, and self-renewing. Every galaxy that spins, every photon that redshifts, every wave that ripples through space participates in this eternal equilibrium. The universe endures not because it resists decay, but because it contains no mechanism for decay on its deepest level. Yet this equilibrium, perfect as it seems, still allows motion, radiation, and change. It allows black holes to merge and gravitational waves to travel. To understand how such activity can exist in a system without dissipation, we must look at the way space-time can carry information without losing energy. That path leads us to the next realization, that gravitational waves are not disturbances in a field, but vibrations of reality itself, the pure sound of geometry in motion. The paradox of energy in general relativity reaches its most vivid expression in gravitational radiation. When black holes or neutron stars collide, their orbiting motion produces waves of curvature that spread across the universe. These waves carry measurable energy, but the universe itself shows no sign of depletion. The black holes merge, the geometry settles, and space-time continues unscarred. This is the clearest example of how energy in general relativity is not spent or lost, but reconfigured. Imagine two massive stars orbiting one another. In Newton's world, their motion would be perfectly stable unless something external interfered. In Einstein's world, their dance disturbs space-time, sending out ripples that carry energy away. Over millions of years, those stars spiral closer together as orbital energy is converted into gravitational waves. When they finally collide, the event releases more power in a fraction of a second than all the visible light of all the stars in the observable universe combined. Yet afterward, the gravitational field of the resulting black hole is as pure and perfect as ever. The system radiates, but gravity itself never weakens. This lossless nature arises because the waves are not disturbances moving through a medium, but changes in the medium itself. There is nothing to heat, nothing to resist. The curvature of space-time oscillates, and that oscillation moves outward at the speed of light. Each region of space momentarily stretches and compresses before returning to equilibrium. The wave does not carry matter away, and when it passes, space-time is left exactly as it was before, save for the new configuration of curvature that now represents the merged system. When gravitational waves were first predicted, many doubted they were real. If gravity is geometry, how can geometry radiate? How can space-time itself have waves without something beyond it to oscillate into? Einstein himself wavered on the question, alternating between belief and skepticism. But the mathematics of general relativity was clear. In the right conditions, curvature can propagate as waves, just as sound propagates through air. The difference is that space-time has no friction, no viscosity. It is the most perfect medium imaginable, because it is not a medium at all. The Laser Interferometer Gravitational Wave Observatory confirmed this in 2015. When the signal arrived, it lasted less than a second. Two black holes, each about 30 times the mass of the Sun, merged over 1 billion light-years away, and the resulting wave passed through Earth, stretching space by less than 1,000th of the width of a proton. The detectors recorded the change, and for the first time, humanity heard the sound of space-time itself. It was not a sound in air, but a vibration in the geometry that defines everything. The faint chirp of that signal marked the first direct proof that space-time can move, flex, and transmit energy without losing itself. This event, and the many that have followed, revealed gravity's extraordinary coherence. Even after traveling billions of light years, the waves arrived undistorted, preserving the precise pattern of the collision that produced them. No matter how far they travel, gravitational waves do not scatter or fade. They grow weaker in amplitude as they spread, but this is not dissipation. It is simple geometric dilution, the same energy distributed over a larger area. The total remains constant. The dissipationless quality of gravity is not merely a curiosity, it is a signature of the universe's underlying order. It tells us that space-time operates as a perfect information carrier. Every ripple that crosses the cosmos encodes the history of its source, and nothing along the way can erase that memory. Light can be absorbed or scattered, but gravitational waves pass through everything. Even matter dense enough to stop photons is almost transparent to them. This purity makes them the truest messengers the universe can send. One might compare space-time to a perfect crystal. In a crystal, vibrations can propagate with little or no loss when the structure is pure and ordered. Imperfections cause scattering and heat. But space-time has no imperfections. It is not built of atoms or molecules. Its structure is continuous and self-consistent, defined entirely by the mathematics of curvature. It can vibrate forever without heating or aging because there is nothing within it to disturb the motion. This property also explains why gravity cannot be confined. Electromagnetic fields can be blocked or redirected by materials. Strong and weak nuclear forces are confined to the tiny scales of atoms. Gravity, by contrast, passes through everything and reaches everywhere. Its geometry links the smallest particles to the largest galaxies. It cannot be shielded because there is no separation between the force and the fabric of existence. In the presence of such perfection, the notion of energy becomes secondary. What we call the energy of a gravitational wave is really a measure of how geometry changes over time. The energy does not flow through space. It is the motion of space. When a gravitational wave passes, the geometry oscillates, and when it moves on, the geometry returns to stillness. No heat is created. No exhaustion follows. The field has expressed a change and then resumed its natural balance. This balance is why the universe can sustain gravitational motion indefinitely. Planets continue to orbit, galaxies continue to spin, and clusters continue to dance through the cosmic web. Gravity binds these structures without friction. It maintains their coherence over billions of years. In every place where gravity acts, it does so without resistance, because there is nothing external to resist it. The geometry of the universe interacts only with itself. This self-interaction is gentle and precise. Space-time can curve and fold, but it never breaks. Even in the most extreme conditions, near the event horizon of a black hole, or in the first moments after the Big Bang, the equations remain consistent. The geometry may change wildly, but its internal bookkeeping never fails. Every distortion has a corresponding response that preserves balance. The universe does not lose energy, because energy, in the deepest sense, is a manifestation of geometry's changing shape. If we could step outside the universe and view its total structure, we might see it as a single, self-contained field, a timeless geometry evolving through its own logic. No part would be wasting energy, no part consuming it. The ripples, waves, and motions would all be patterns within the same seamless whole. From within, we experience those patterns as forces, motions, and radiation. But from the outside, there would be only geometry, perfect, coherent, and eternal. This is the essence of the energy paradox. Gravity seems to radiate, yet it never weakens. It seems to move, yet it never expends. It shapes everything, yet it remains untouched. The secret lies in the nature of geometry itself. It is not a process unfolding within space and time, but the definition of space and time. What we call motion is the unfolding of this definition. Understanding this leads naturally to the next revelation. If space-time behaves like a perfect crystal, coherent, self-sustaining, and lossless, then perhaps it also obeys laws akin to thermodynamics. The connection between curvature, temperature, and entropy, first glimpsed in the physics of black holes, suggests that space-time may have an internal equilibrium. Gravity's dissipationless nature could arise because the universe is already in a state of cosmic balance, a thermal harmony where change occurs without loss. In the quiet reaches of the universe, where galaxies drift like luminous islands in a black sea, the geometry of reality itself is alive with motion. It vibrates, trembles, and sings, though not in any frequency that ears can hear. These vibrations are the whispers of gravity in motion, ripples in the fabric of space-time that travel across billions of light years without losing their purity. The existence of such waves was first predicted in the early years of the 20th century, as Einstein explored the implications of his field equations. If space-time could bend, it could also flex. If it could flex, then changes in one region should propagate outward, carrying information about the motion that created them. But for decades, this remained only a mathematical curiosity. The waves were thought to be impossibly faint, their effects too small to ever measure. It took a century of ingenuity to prove that space-time truly ripples. The Laser Interferometer. Gravitational Wave Observatory, two immense detectors set thousands of kilometers apart, was built for this purpose. Each arm of the detector was 4 kilometers long, and each beam of light within it could measure distances with unimaginable precision. When the first signal arrived on Earth in September of 2015, the instruments quivered for less than a second. The event had occurred more than 1 billion years earlier, when two black holes, each about 30 times the mass of the Sun, had merged into one. The faint distortion that reached us changed the length of each laser path by less than 1,000th the width of a proton. Yet in that minute signal lay confirmation that space-time itself could move. The discovery was more than a triumph of technology. It was a revelation about the nature of the universe. Gravitational waves are not carried by a medium. They are the medium in motion. When such a wave passes, space does not contain the disturbance. Space is the disturbance. The distance between 2 points briefly changes because the geometry connecting them changes. There is no transfer of energy through friction or resistance. The wave glides through reality with perfect grace. This purity makes gravity unlike any other phenomenon. Electromagnetic waves, light, radio, and X-rays, can be absorbed, scattered, or reflected. Their photons interact readily with matter. Gravitational waves, however, pass through stars, planets, and even neutron stars almost unimpeded. Their interaction with matter is so weak that they carry information across cosmic distances without distortion. The same wave that left a black hole billions of years ago arrives at Earth nearly unchanged. This dissipationless nature is astonishing. In the physical world we know, every form of motion eventually fades. Vibrations in air die into silence. Currents in metal generate heat. Even light, spreading outward, becomes weaker with distance. But gravity's waves endure. They do not weaken from friction, but only by dilution. Their amplitude spreads as the sphere of space-time they occupy grows. Their purity remains absolute. This means that gravitational waves carry with them perfect information about their source. Each wave encodes the story of its birth, the masses involved, the shape of their orbits, the moment of collision. When physicists study these waves, they are reading the signature of cosmic events written directly into the structure of space-time. They are not observing reflections or emissions, but the true motion of the universe itself. And yet, even as these waves carry energy, they do not diminish gravity as a whole. The field that gives rise to them is infinite and self-sustaining. The black holes that emit the waves lose orbital energy, but the geometry that defines gravity continues unaltered. Space-time does not tire. It can bend, stretch, and ripple endlessly without loss because there is nothing external to absorb its motion. To call gravitational waves the sound of space-time is more than metaphor. Sound is a pattern of vibration, a pressure wave moving through air. Gravity's waves are vibrations of curvature itself. They are the notes played by the universe's own geometry. When black holes collide, space-time rings like a vast, invisible instrument. Each note carries across eternity without static or decay. The dissipationless nature of gravity reveals a deeper symmetry. In every physical system, dissipation arises from friction, from interactions between independent components. But space-time has no components in that sense. It is continuous, self-contained, and complete. There is no separate structure for energy to leak into. When curvature changes, it does so holistically. The geometry evolves, but the total remains balanced. This perfect coherence also explains why gravity can dominate the universe across all scales. It is the weakest of the fundamental interactions when measured locally, yet it shapes the largest structures in existence. While other forces fade with distance or cancel through polarity, gravity's reach is unbounded. It is everywhere, eternal, and lossless. The power of gravitational waves also demonstrates how deeply energy and geometry are entwined. In classical physics, energy is something that moves through space. In general relativity, energy is the motion of space itself. When gravitational waves travel, they do not carry a fluid of energy. They carry a pattern of curvature. That pattern changes the geometry as it passes, redistributing what we call energy, but never consuming it. In this sense, the universe's most violent events are paradoxically the most peaceful. A black hole merger radiates unimaginable power, yet the fabric of space-time itself remains serene. After the waves pass, the geometry settles into perfect equilibrium. There are no remnants of heat, no leftover vibrations, no decay of structure. The event is recorded, but not at the cost of the universe's balance. When physicists say that gravitational waves carry energy, they are using a word that belongs to a world of measurements and exchanges. But on the scale of space-time, energy is geometry's memory of motion. It is not stored or spent. It is simply the measure of how curvature evolves. The universe is not a furnace burning fuel. It is a symphony of shapes, changing in harmony. This understanding reshapes our idea of endurance. Gravity does not last because it resists time. It lasts because it is time, the continuous unfolding of space-time's form. The geometry of the cosmos endures because it is the definition of continuity itself. If the universe is an orchestra, then gravity is its rhythm, the deep and unending bass line that guides every motion. The other forces may flicker like notes of melody, but gravity is the structure upon which they play. Its waves are not disruptions, but confirmations, proof that the fabric of existence is alive and unbroken. To move forward, we must now ask a more profound question. If space-time can ripple like a perfect fluid, what prevents those ripples from ever decaying? What property of reality keeps geometry so pure, so lossless? The answer lies in the very nature of gravity's field, a phenomenon that seems to behave like a superconductor of curvature, immune to dissipation, bound by symmetry, and eternally self-sustaining. Gravitational waves travel through the universe as pure geometry in motion, and yet they interact with everything they touch. The paradox lies in how they can do so without leaving a mark. When a wave passes through a planet, the distances between every atom expand and contract, but only by an amount far smaller than a proton's width. The planet feels this cosmic tremor, yet no heat is produced, no stress remains afterward. The wave leaves no trace because space-time itself, unlike matter, has no internal structure to resist or absorb motion. This is what it means for gravity to be dissipationless. It does not trade energy with its environment. It redefines the environment. It cannot be slowed or dampened because there is no external medium to sap its strength. The wave does not move through space. It is space moving. Its existence is a pure oscillation of geometry. In the world of electromagnetism, every motion of charge creates radiation. When a current flows through a wire, electrons collide with atoms and lose energy as heat. This is dissipation, the conversion of ordered motion into disorder. But gravity operates on a deeper level of order, one in which no such conversion can occur. There is no microscopic chaos inside spacetime, no atoms or grains for motion to scatter against. The curvature can oscillate, but it never stumbles. Physicists often describe gravity's self-interaction as remarkably weak. When electromagnetic waves cross, they can interfere, exchange energy, or scatter. Gravitational waves, in contrast, pass through one another almost untouched. Even two waves, of enormous amplitude, the kind produced by colliding black holes, can overlap, cross paths, and continue as though they had never met. This near transparency is not weakness in the ordinary sense. It is perfection. The waves carry energy as pure geometry, and geometry has no need to exchange or dissipate that energy. This makes space-time the universe's most flawless medium. It is immune to turbulence, immune to viscosity, and immune to decay. A wave in space-time may stretch to cosmic scales, but it never frays. Its information content, the detailed pattern of oscillation, remains intact across unimaginable distances. The universe has endured for over 13 billion years, yet gravitational waves that began near its dawn still move through it today, undimmed and uncorrupted. If the cosmos were filled with matter dense enough to interact strongly with these waves, they would have long since faded. But the density of the universe is so low, and the coupling between gravity and matter so extraordinarily weak, that the waves glide through unhindered. Even the densest neutron star is nearly transparent to them. The entire universe is, in a sense, a perfect transmission line for gravitational information. This perfection invites comparison with phenomena in quantum physics. In superconductors, electric current flows forever without resistance. In superfluids, motion continues without friction. These systems achieve their perfection through coherence, a quantum condition in which all particles act as one. Their collective behavior cancels dissipation. Gravity seems to be the cosmic analog, a superfluid of geometry, a superconducting field that moves without loss. The idea that space-time might behave like a superfluid is not metaphorical whimsy. Some physicists have explored it as a literal hypothesis. In these models, the curvature of space arises from the flow of an underlying quantum condensate, a vast, invisible ocean whose movements define what we perceive as gravity. If true, this would explain why gravitational waves travel without loss. They are the sound waves of this superfluid cosmos. But unlike any ordinary fluid, space-time cannot heat or cool, cannot thicken or thin. Its flow is perfectly self-regulated. The dissipationless quality of gravity might therefore be more than a coincidence. It might be a clue to the universe's fundamental state. Every ripple of curvature could be a collective quantum motion, spreading through a vacuum that is itself perfectly coherent. Even in the classical theory, this coherence shows itself. When we describe a gravitational wave mathematically, we find that it satisfies a wave equation with no term for resistance. The propagation is ideal. It requires no replenishment of energy because the wave is not something traveling within space-time. It is space-time itself changing shape. There is no background that could drain it. The wave's persistence is simply the persistence of geometry. To visualize this, imagine a sheet of water frozen in perfect stillness. If a ripple moves across it, the motion is not the movement of the water from one side to another, but a local rise and fall that passes along. Afterward, the surface is exactly as it was before. Gravity behaves like this, but in 4 dimensions. Its ripples are distortions of spacetime's curvature, momentary changes that return to equilibrium without waste. This property has astonishing consequences. It means that gravity, unlike all other fields, does not age. It is as fresh today as it was at the universe's birth. The light of early stars has long faded, absorbed by dust or stretched beyond visibility, but gravity's imprint from that time still flows undisturbed. The universe's oldest story is not written in light, but in the shape of spacetime itself. And because gravitational waves interact so weakly with matter, they provide a unique way to probe the cosmos. They carry not the surface details of stars or galaxies, but the raw imprint of motion and mass. Each passing wave is a message written directly in geometry, a piece of the universe's memory that no force can erase. The dissipationless nature of gravity also implies that it may play a special role in the preservation of information. In quantum theory, the loss of information through dissipation or entropy is tied to the irreversible arrow of time. But if gravity propagates without loss, then it may form the foundation upon which time's arrow rests, a timeless structure through which all change occurs, but which itself never changes in kind. In this sense, gravity's perfection is not merely physical, but existential. It provides the continuity that allows the universe to exist as a coherent whole. The stars burn, the galaxies evolve, entropy increases, but gravity remains. It does not tire or degrade because it is the framework of degradation itself. Time, entropy, and change unfold within its geometry, but gravity does not partake in their decay. And yet, there are places in the universe where gravity seems to reveal a thermodynamic face: black holes. These regions appear to possess temperature and entropy, to radiate energy, and even to evaporate. If space-time can be perfectly lossless everywhere else, how can it become thermodynamic at an event horizon? The answer may hold the key to understanding why gravity's dissipationless nature exists at all. Perhaps what we call dissipation and what we call equilibrium are 2 sides of the same law. Gravity might be lossless because, on a cosmic scale, it is already in perfect thermal balance. The next step in our journey leads to this paradox: the discovery that space-time, though it never tires, may have a hidden temperature of its own. The realization that gravity moves without friction challenges every intuition formed in a world of resistance. In daily life, energy is the currency of change, and every action carries a cost. A spinning wheel slows, a pendulum stops, a pulse of light fades into background heat. Motion seems to demand sacrifice. Yet gravity alone defies this rule. It acts, shapes, and carries information without expenditure. It is the perfect traveler, the messenger that never grows weary. When a gravitational wave leaves its source, it carries a precise rhythm of motion, a pulse of curvature defined by the masses and paths that created it. As it crosses the universe, this rhythm remains perfect. Each crest and trough of space-time arrives as it was formed, 1 billion years old, yet unaged. The signal does not echo or distort. It is not absorbed by dust or plasma, nor scattered by stars. It flows through all of them as though they were shadows in its path. This makes gravitational observation a form of cosmic archaeology unlike any other. Light can reveal what an object looks like, but gravity reveals what the universe is doing. When detectors on Earth capture a gravitational signal, they are not seeing the surface of an event. They are feeling the tremor of reality itself. The wave is not a representation of the merger of black holes. It is that merger, translated into motion within our own space-time. Each detection proves that gravity is the universe's memory, written in a script of geometry. Every ripple that moves through the cosmos is a preserved moment of interaction between matter and curvature. Unlike light, which can be destroyed, these waves cannot truly vanish. They stretch and fade with distance, but they are not erased. The universe may be filled with such echoes, relics of ancient collapses, cosmic births, and violent unions, still moving silently through the dark. And yet, despite this ceaseless motion, the universe does not tire. The waves do not accumulate heat or noise. There is no background hum of spent energy weighing upon space-time. The cosmos expands and evolves, but its geometry remains poised in perfect balance. It is as though space-time itself is an eternal sea, stirred but never disturbed. This perfection invites a comparison that is more than poetic. Gravity behaves as though it is the universe's most ideal superfluid. In superfluid helium, motion continues without viscosity. Vortices can circle endlessly without decay. In superconductors, electric current flows without resistance because all particles move in quantum harmony. Gravity mirrors both behaviors, but on the scale of reality itself. Its waves move through the cosmic fabric without friction, their coherence absolute. If space-time is indeed a kind of quantum fluid, it is one that flows without ever breaking coherence. Such a picture raises an extraordinary possibility. If the vacuum behaves like a perfect superfluid, then the dissipationless nature of gravity might be a direct expression of the universe's quantum order. The gravitational field would then be not an external force, but a collective state of the vacuum itself, a manifestation of underlying coherence that cannot dissipate because it has no substructure to disturb it. This view harmonizes beautifully with the mathematical purity of Einstein's equations. Those equations have no terms for decay, no frictional constants, no coefficients for loss. They describe a geometry that evolves but does not erode. The solutions are timeless. Even when gravitational waves travel through the universe, they are governed by linear, symmetric equations that preserve form and information. The waves can interfere and add, but they cannot cancel or destroy each other. Their superposition is perfect. One of the most striking confirmations of this comes from the binary pulsar, known as PSR 1913+16. Discovered in the 1970s, this pair of neutron stars orbits each other with extraordinary regularity. Over the decades, astronomers observed that their orbit slowly shrinks, exactly as predicted if gravitational waves are carrying energy away. The rate of decay matches Einstein's formula with astonishing precision. Yet this energy is not lost into nothingness. It is redistributed as space-time waves that travel forever. The universe's energy accounting remains flawless. The motion changes form, not magnitude. Such precision demonstrates a kind of universal discipline. Every curve, every pulse of gravity obeys a rule of perfect consistency. It is as if space-time itself enforces a code of conduct, to move but never to waste, to oscillate but never to tire. This discipline may be the reason why gravity endures across cosmic time. It is not merely a field acting within the universe. It is the universe's structure maintaining its own equilibrium. When scientists say that gravitational waves carry energy, they speak from within the limited framework of measurement. They quantify how much mass-equivalent curvature moves from one region to another. But to the universe, this is not a transaction. It is choreography. The energy is not spent. It is transformed in a self-sustaining rhythm. The universe dances, but the dancer never grows weary. In this view, gravity's dissipationless nature becomes not just a feature of general relativity, but a principle of existence. It ensures that the cosmos can evolve without consuming itself. Galaxies can orbit for billions of years. Clusters can drift. Space-time can expand. The underlying geometry provides the continuity that allows everything else to change. Without this perfect balance, the universe would unravel into chaos or freeze into stillness. Gravity is the rhythm that keeps creation in motion without decay. And yet, the same geometry that flows so effortlessly can reveal another face. One that hints at heat, entropy, and even evaporation. Black holes, those ultimate creations of gravity, seem to violate the rule of losslessness. They radiate energy, possess temperature, and embody entropy. How can something born from a dissipationless field display thermodynamic behavior? The paradox is only apparent. It suggests that gravity's perfection might not exclude thermodynamics, but instead arise from it. If spacetime is in a state of deep equilibrium, then black holes could be its boundaries, regions where that equilibrium becomes measurable. Their heat and entropy might be the visible surface of an otherwise invisible thermal harmony pervading the cosmos. Thus, the next stage of our journey turns toward the thermodynamics of spacetime itself. From Bekenstein and Hawking's revelations, to Jacobson's profound insight that Einstein's equations might be laws of heat balance, we begin to glimpse the possibility that gravity's endurance comes not from defying thermodynamics, but from embodying it perfectly. Everywhere in the universe, motion eventually fades. Friction slows the spinning wheel. Heat drains from the cooling star, and even light itself grows weary as it travels across the expanding cosmos. Yet one thing endures untouched by time: gravity. It holds galaxies together for billions of years without faltering. It guides stars around black holes and planets around stars with unbroken precision. No matter how long the universe lasts, gravity never grows weaker, never burns out, and never loses its perfect rhythm. To understand this endurance, we must look closely at what it means for something to be dissipationless. Dissipation is the process through which energy transforms into disorder, the conversion of useful motion into heat. It is what gives the arrow of time its direction, the tendency of systems to move from order toward chaos. But gravity, as far as we can tell, does not follow that rule. It can radiate, it can ripple, but it does not decay. When gravitational waves move through space, they spread but do not tire. Their form remains pure, their energy undiluted except by the geometry of distance. This purity arises from gravity's unusual status in physics. It is not a force in the ordinary sense, not a field superimposed upon a background, but the background itself, the geometry of reality. All forms of motion take place within spacetime, but gravity is spacetime. Because of this, it has no external environment into which it can dissipate. There is nothing beyond gravity that could absorb its energy or disrupt its coherence. When spacetime curves, it is simply changing its own shape. The process cannot waste energy because energy, in this context, is defined by the very curvature that is evolving. Imagine a wave passing through the ocean. The water beneath it moves only slightly, rising and falling as the shape of the surface changes. After the wave has gone, the water is the same as before. In a similar way, when gravitational curvature ripples through the cosmos, the universe flexes and then returns to equilibrium. The geometry has moved, but nothing has been consumed. Other forces cannot achieve this. Electromagnetism, for instance, interacts with matter at every step. Photons collide with atoms, lose energy, and create heat. Strong and weak nuclear forces operate at small scales and constantly convert one form of particle energy into another. Gravity alone moves without obstruction. Its coupling to matter is so faint that even a wave passing through a neutron star is hardly disturbed. It neither deposits nor absorbs measurable energy. It simply passes through, leaving space-time perfectly smooth. This dissipationless nature also explains why gravity can connect the largest structures in the cosmos. While light can be blocked by dust or absorbed by matter, gravity passes through everything. Its reach is infinite, its influence unbroken. It is the only interaction that cannot be screened or cancelled. A planet's pull cannot be neutralized. A star's curvature cannot be erased. The universe's web of galaxies and clusters exists because gravity's grip does not weaken with time or obstruction. In the language of physics, gravity is self-consistent. Its equations contain no terms for friction, resistance, or loss. The Einstein field equations describe a system in perfect balance. Curvature evolves according to the distribution of matter and energy, and matter moves according to curvature. This mutual definition ensures that the system remains closed and coherent. There is no external reservoir where energy could vanish. One can think of this in terms of a perfect dance. Each movement of matter creates a change in curvature, and each change in curvature guides the next motion of matter. The two are locked in eternal choreography, exchanging roles but never losing synchronization. Because both partners are part of the same system, there can be no true dissipation. Nothing leaves the dance floor. The energy of motion is geometry itself. This explains why gravitational systems can persist for billions of years. The orbits of planets decay only through extremely small effects like tidal forces or the emission of gravitational radiation. Processes so slow that they hardly touch the structure of spacetime itself. The planets continue circling their stars as they have for eons because spacetime gives them a perfect path to follow, one that does not require constant expenditure of energy. In general relativity, motion along a geodesic, the natural path in curved spacetime, is effortless. An object following such a path experiences no force and no loss. From the smallest orbit to the largest galactic structure, this same rule applies. The stars move within the gravitational wells of their galaxies as if gliding along invisible rails. The galaxies themselves are bound together in clusters and superclusters, drawn into cosmic filaments that extend across hundreds of millions of light years. The web of the universe is woven by gravity's endurance, a network that never frays, even as the universe expands. It is tempting to ask what allows this perfection to exist. In the physical world we inhabit, every process that involves energy seems to involve entropy, the gradual dispersal of order into randomness. But gravity operates differently. Instead of dispersing, it organizes. It draws matter together, forming stars, planets, and galaxies out of primordial chaos. While other interactions drive systems toward equilibrium, gravity creates structure from uniformity. It is the only known phenomenon that reverses the usual direction of entropy on large scales. This does not mean that gravity violates thermodynamics. Rather, it redefines what equilibrium means. A self-gravitating system like a star cluster reaches a kind of stable state, not when it spreads evenly, but when it finds a balance between attraction and motion. Gravity's version of equilibrium is dynamic, a constant reshaping that never stops, but also never dissipates. The energy within it cycles endlessly, converting between motion and curvature without ever leaking away. Even when gravity radiates, as in the case of merging black holes, the process remains pure. The energy emitted in gravitational waves does not come from within gravity itself. It comes from the changing configuration of the system's mass and momentum. The geometry shifts, and the waves carry that change outward. Yet, the underlying field, space-time, does not fade. It adapts, adjusts, and continues unaltered. This makes gravity the most remarkable phenomenon in the cosmos, a field that can transmit energy yet never lose its own integrity. It is the only known interaction that exists both as a dynamic process and as the stage for all other processes. It is the silent foundation upon which all motion plays out, immune to decay, because it is the definition of persistence. If the electromagnetic field is like a sea of light and charge, gravity is the sea itself, an endless, borderless continuum that cannot run dry. Its dissipationless nature ensures that the universe remains coherent from its birth until its eventual fate. When everything else grows cold and still, the geometry of space-time will continue to shape what remains. But the question deepens. Why does gravity resist dissipation so completely? Is its perfection a coincidence of geometry, or does it reveal something fundamental about the nature of the vacuum itself? Perhaps the answer lies in the very structure of space-time, in the way it encodes temperature, entropy, and equilibrium on a cosmic scale. To understand this, we must look at how gravity intertwines with thermodynamics, and how the universe's most perfect field may already exist in a state of eternal balance. Gravity's resistance to dissipation is not only a quirk of geometry, but a profound clue about the underlying nature of space-time itself. The universe, on its deepest level, appears to be built upon principles of balance so perfect that energy can move endlessly without loss. To see this clearly, we must examine how the gravitational field maintains coherence across every scale, from the tiniest ripple to the grandest galactic flow, and why it behaves more like a living equilibrium than a mechanical process. When two stars orbit each other, they disturb space-time, sending gravitational waves into the universe. Those waves travel at the speed of light, stretching and compressing everything they pass through. But even after billions of light years, they remain precise echoes of their origin. They do not scatter as sound does in air. They do not fade the way light does when it meets dust. This purity is not merely an accident of weakness. It is a sign of fundamental harmony. Gravity, by its nature, couples universally but feebly, ensuring that nothing can disrupt its motion, yet everything must obey it. If space-time could lose energy internally, if curvature could rub against itself and generate heat, the universe would have long since changed beyond recognition. The cosmic web would blur, black holes would dissolve, and orbits would decay into stillness. But none of this happens. Instead, space-time flows through eons as though immune to wear. Galaxies form, merge, and evolve within it. Yet the gravitational field remains unbroken. It is not just stable, it is timeless. This is why some theorists compare gravity to a superfluid. In a superfluid, particles move in perfect coordination, a collective quantum state that allows motion without resistance. There is no internal friction, no scattering of energy into heat. The fluid can swirl forever, preserving its coherence as though time itself had stopped within it. Space-time seems to exhibit the same perfection, though on a scale far greater and with a mechanism we do not yet fully understand. Its flow of curvature, its propagation of waves, and its capacity to maintain structure over cosmic time all point to a medium in perfect equilibrium. If this analogy holds true, then space-time may not be an inert backdrop but a living quantum state, a sea of coherence so vast that its smallest disturbances correspond to the ripples we call gravity. The apparent strength or weakness of gravity might then be a measure of how stiff this quantum fluid is, how resistant it is to being disturbed. Its dissipationless behavior would follow naturally, because a perfectly coherent state cannot lose information to internal noise. This connection between gravity and information may hold the key. In modern physics, information is as fundamental as energy. It cannot be created or destroyed, only transformed. If space-time itself is an information field, a fabric whose curvature encodes the history of energy and motion, then its dissipationless nature becomes inevitable. Information can flow through it, but it cannot vanish. The ripples we call gravitational waves are simply patterns of information rearranging themselves. No loss occurs because no part of the system lies outside the flow. This principle appears vividly in the study of black holes. According to classical physics, a black hole should be the ultimate absorber, a region from which nothing, not even light, can escape. Yet even black holes do not violate gravity's dissipationless law. Their horizons radiate faintly, a glow predicted by quantum mechanics and known as Hawking radiation. This radiation does not represent decay in the gravitational field itself, but a conversion of curvature into quantum information. The geometry adjusts, but the overall balance remains exact. The more we study gravity, the more it seems to reveal a cosmic self-symmetry. Every interaction that could cause loss or imbalance is mirrored by another that restores harmony. When gravitational energy leaves a system in waves, the geometry that created those waves shifts in just the right way to preserve consistency. No matter how complex the process, the total remains unchanged. It is as though space-time carries within it an internal rule, a conservation deeper than energy itself. In ordinary materials, dissipation arises from microscopic disorder. A moving object transfers its energy to countless smaller degrees of freedom, atoms, vibrations, random motions that scatter energy into heat. Spacetime, however, seems to lack those hidden degrees of freedom. Its structure is continuous, or at least behaves as if it were. There are no small constituents to absorb motion. Every oscillation, every gravitational wave is a motion of the whole. This absence of substructure is the reason for its perfection. And yet, quantum physics hints that spacetime might not be perfectly continuous after all. On scales far smaller than atoms, the vacuum may possess texture, a sea of quantum fluctuations, fields rising and falling in endless, chaotic energy. Paradoxically, even this restless vacuum does not dissipate gravity. Instead, it interacts with it in a perfectly balanced way. The fluctuations contribute to curvature, but never absorb gravitational energy. The vacuum, though seething with activity, is transparent to gravity's flow. It neither drags on it nor amplifies it. This delicate balance suggests that gravity and the vacuum are deeply entangled. They form a closed loop of interaction where each defines the other. The vacuum provides the stage for geometry. Geometry provides the rules for the vacuum's fluctuations. Because of this unity, no energy is lost between them. What one gives, the other returns. The universe, at its foundation, is a system without waste. To speak of dissipationless gravity, then, is to speak of the universe as a perfect ledger, one that records every change without error or loss. The curvature of space-time is not merely a mathematical surface, it is the memory of all motion, conserved in form forever. Even when black holes collide, when entire galaxies merge, or when stars collapse into singularities, the information contained in curvature remains encoded in the evolving geometry. Nothing vanishes. This is why, in the far future, when the stars have burned out and the universe has grown cold, gravity will still endure. The cosmic dance may slow, the galaxies may drift apart, but the structure of space-time will persist, carrying within it the record of everything that has ever occurred. The waves may stretch into infinity, their amplitude thinning to whispers beyond detection, but their form will remain perfect, like faint ripples still moving across a pond long after the stone has sunk. The dissipationless nature of gravity is thus not merely a feature of general relativity. It is a principle of existence itself. The universe is not a machine wearing down, but a geometry unfolding in endless coherence. Space-time is not eroded by the passage of time. It is the passage of time, the ever-renewing balance that allows motion, change, and memory to coexist without loss. Yet, even this perfection hides a question. If gravity is lossless because it is already in equilibrium, then equilibrium itself must have meaning on a cosmic scale. What does it mean for space-time to be at rest thermodynamically? Can we speak of temperature or entropy for a field that never dissipates? These are not idle speculations, for black holes and quantum theory hint that space-time may indeed possess its own thermodynamic identity. To understand why gravity never tires, we must see that it may not need to. Its dissipationless nature could be the result of a deeper balance, a universal thermal symmetry that makes space-time both dynamic and eternally calm. And so our path leads next to the discovery that space-time is not merely geometry, but also a kind of heat, a thermodynamic sea, whose equilibrium defines reality itself. Gravity's dissipationless quality reveals something extraordinary about the relationship between geometry, motion, and time. It tells us that the universe itself may be structured not as a machine that winds down, but as a self-maintaining equilibrium, an eternal engine that neither consumes nor wastes. This realization changes how we see not only gravity, but the very idea of energy. In every known physical system, energy is both the measure and the limit of motion. It is what allows transformation and what enforces decay. But gravity operates outside this balance. It connects all energy without belonging to it. When mass curves space-time, It does not spend energy to do so. It simply is energy in another form. When two black holes spiral together and send waves across the cosmos, the process transfers curvature into motion and back again, with perfect bookkeeping. Nothing leaks away. This is why attempts to define gravitational energy often lead to paradoxes. In general relativity, energy is not globally conserved in the way it is in Newtonian physics. Instead, conservation is local. It holds true within each region of spacetime, but not necessarily across the entire cosmos. The geometry can stretch, expand, and reshape itself, apparently without any cost. Yet this is not a violation of physics. It is a sign that energy and geometry are two languages describing the same story. If gravity is the manifestation of space-time geometry, then dissipationlessness is not a property of a force, but of the fabric of existence. The reason it does not lose energy is that it has no outside. There is nowhere for its energy to go. The universe cannot radiate curvature into something beyond itself because there is nothing beyond. The energy that appears to leave one region simply becomes the structure of another. This self-contained nature of space-time leads to the idea that gravity might represent a perfect conservation of information rather than energy. In physics, the loss of energy often coincides with the loss of information. When heat is generated, the microscopic details of motion become scrambled beyond recovery. But gravity resists this. Its waves preserve detail with incredible fidelity. A gravitational signal encodes the mass, spin, and trajectory of its source down to the finest degree. Even after traveling for billions of years, that information remains unblurred. Such perfection hints at a deeper law. If the universe were truly dissipative at its core, every interaction would slowly erase memory, and time itself would eventually lose meaning. The arrow of time depends on the growth of entropy, on the gradual degradation of order. Yet gravity appears to exist outside this process, acting as a timeless foundation upon which entropy unfolds. It might be that time's arrow emerges from the asymmetry of matter and radiation, while gravity remains the eternal backdrop, the unchanging stage on which change occurs. This makes the dissipationless nature of gravity more than a technical detail. It is a clue to the unity of the cosmos. The same perfection that allows waves to travel without loss may be what keeps the universe stable on the largest scales. Expansion, structure formation, and even the cosmic microwave background all trace their patterns back to gravity's coherence. Without it, the universe would dissolve into thermodynamic chaos. With it, the cosmos remains ordered enough for stars to burn and for life to think. In this way, gravity behaves as though it enforces a cosmic equilibrium. It does not resist change, but it ensures that change is reversible, at least in principle. Even black holes, which seem to destroy information, may ultimately obey this rule. The discovery of Hawking radiation suggested that black holes can evaporate, releasing energy in the form of heat. Yet deeper theories now propose that the information swallowed by a black hole is not lost, but encoded in its quantum surface, a holographic imprint of everything it has consumed. If this is true, then even the most extreme gravitational process is dissipationless at its core. Perhaps then, gravity's perfection is the signature of the universe's ultimate conservation law, one that extends beyond energy to include geometry and information themselves. In this view, space-time is not merely a passive stage, but an active, self-regulating system. Every vibration, every curvature, every gravitational wave is part of a grand equilibrium that maintains itself eternally. The dissipationless theory of gravity suggests that the universe does not need replenishment because it is already complete. Motion and stillness, energy and curvature, cause and effect, all are facets of a single self-sustaining whole. Gravity's endurance is the expression of that completeness. It is not fighting against decay, it exists beyond decay. And yet, this perfection, invites one final mystery. If spacetime can act as a thermodynamic system with temperature and entropy, as black hole physics shows, then the dissipationless nature of gravity might not be a contradiction, but a revelation. It could mean that the universe, on its largest scale, has reached a perfect state of balance, a thermodynamic calm in which every local change is counterbalanced by a global stillness. To explore that possibility, we must turn to the thermodynamics of spacetime itself, where the boundaries between heat, geometry, and gravity dissolve into one. There, the story of dissipationless gravity deepens, showing us that spacetime may not just avoid entropy, but may be entropy, an equilibrium so complete that it never needs to rest. Long before physicists understood black holes as physical objects, they were seen as mathematical curiosities, strange singularities hidden behind horizons from which nothing could escape. They were symbols of finality, places where time stopped and all known laws of nature broke down. Yet, by the closing decades of the 20th century, a remarkable discovery transformed black holes from cosmic tombs into living thermodynamic systems. It was realized that these regions of infinite darkness possess temperature, entropy, and even a faint form of radiation. From that realization, a deeper truth began to emerge. Gravity itself might be a thermodynamic phenomenon, and the entire fabric of spacetime could be governed by principles of heat and equilibrium. To grasp this transformation, one must first understand how black holes became the laboratories of gravity's deepest mysteries. In the early 1970s, Jacob Bekenstein proposed that a black hole, despite appearing to be a region of complete nothingness, should carry entropy proportional to the area of its event horizon. Entropy is a measure of disorder or information, of how many microscopic configurations could exist for a given macroscopic state. If black holes truly destroyed information, as classical physics seemed to suggest, they would violate the most sacred rule of thermodynamics, that entropy in a closed system must never decrease. To restore that balance, Bekenstein suggested that the event horizon must encode information about everything that falls into it, preserving the record of the universe's history. This radical idea gained extraordinary support when Stephen Hawking performed his now famous calculation in 1974. By combining quantum mechanics with general relativity, he found that black holes are not entirely black. They emit a faint glow of thermal radiation due to quantum fluctuations near the event horizon. This Hawking radiation implied that black holes have a temperature and therefore an entropy proportional to the surface area of their horizon, measured in units of the Planck length squared. The surface, not the volume, held the information. The black hole's event horizon was revealed as a thermodynamic boundary, a shimmering membrane encoding the heat and entropy of the gravitational field itself. From that point forward, the connection between gravity and thermodynamics could no longer be ignored. Every physical quantity associated with black holes fit perfectly into the classical laws of thermodynamics. The surface gravity of the black hole played the role of temperature. The area of its horizon represented entropy, and changes in mass, rotation, and charge obeyed a first law, analogous to the familiar equation of energy balance. It was as if space-time itself obeyed the same logic as steam in a piston or light in a cavity, an engine governed by the exchange of heat and work. Yet, unlike ordinary systems, the thermodynamics of space-time is not about the agitation of particles, but the configuration of geometry. The microscopic degrees of freedom that give rise to this entropy are not yet known. They may be quantum states of space-time itself, vibrations of geometry on scales so small that distance and time lose their meaning. But whatever their nature, they must exist. Without them, the universe could not satisfy the same fundamental laws that govern everything else. The realization that space-time possesses temperature and entropy changed how we think about gravity. It revealed that general relativity might not be the ultimate theory of gravitation, but a large-scale statistical description, like thermodynamics itself. In the same way that temperature and pressure emerge from the collective behavior of countless molecules, Einstein's equations might emerge from the collective behavior of microscopic space-time degrees of freedom. Gravity, in this view, is not a fundamental force, but an emergent one, the macroscopic shadow of deeper quantum dynamics. This interpretation found its most elegant expression in 1995, when physicist Ted Jacobson demonstrated that Einstein's field equations can be derived directly from the laws of thermodynamics. By assuming that entropy is proportional to the area of local Rindler horizons, the boundaries of spacetime experienced by accelerated observers, Jacobson showed that the relation between heat, entropy, and energy flow leads naturally to the Einstein equations themselves. The curvature of spacetime, in other words, is the result of thermodynamic balance. Where heat flows, geometry bends. Where energy crosses a horizon, spacetime responds to maintain equilibrium. Gravity is not imposed upon spacetime. It is the manifestation of spacetime's attempt to keep its thermodynamic books balanced. This insight turned the universe inside out. It suggested that the geometry of spacetime is the macroscopic expression of an underlying microstructure, just as the smooth behavior of air emerges from invisible molecules. It also explained why gravity is dissipationless. If spacetime is already in thermal equilibrium at a fundamental level, then its large-scale behavior must be perfectly lossless. A system in complete equilibrium does not dissipate energy, it merely adjusts its configuration when disturbed, restoring balance without loss. The event horizon of a black hole is a window into this equilibrium. It marks the place where information and energy exchange between the interior and exterior are encoded as thermodynamic quantities. When matter falls into a black hole, the increase in horizon area ensures that the second law of thermodynamics remains intact. The system's total entropy never decreases. Yet the process is entirely reversible in principle. If Hawking radiation allows the black hole to evaporate, the information hidden in its horizon must somehow return to the universe, perhaps subtly encoded in the radiation itself. Gravity's apparent dissipation, the swallowing of matter by black holes, may therefore be an illusion. On the deepest level, nothing is lost. The universe continues to conserve its information perfectly. Thermodynamics also explains the mysterious simplicity of black holes. Despite being composed of potentially infinite configurations of matter and energy, a black hole is described by only a few macroscopic quantities: mass, spin, and charge. This economy mirrors the universality of thermodynamic systems, where temperature and pressure summarize vast complexity. Gravity, too, seems to condense the richness of its microscopic underpinnings into a few geometric variables. If spacetime is a thermodynamic system, then temperature itself may be a property of geometry. Acceleration, for instance, creates an apparent horizon, a boundary beyond which events cannot be observed. An observer accelerating through empty space perceives a warm glow known as the Unruh temperature, a faint heat that arises purely from motion. This effect demonstrates that temperature can emerge from geometry and perspective, not from matter. The same logic applies to black holes and to the expanding universe as a whole. The temperature of spacetime is a measure of curvature and acceleration, not of molecular agitation. In this light, gravity's dissipationless character takes on a new meaning. It is not that spacetime is immune to thermodynamics, but that it is thermodynamics in perfect balance. Every curvature, every wave, every gravitational interaction represents an exchange of energy that obeys the same logic as heat flow, yet without any net loss. The universe maintains its overall equilibrium, even as local processes unfold within it. In the language of thermodynamics, spacetime's entropy is already maximized. The cosmos as a whole exists at the edge of perfect balance, the ultimate equilibrium from which all motion arises. This perspective transforms our understanding of the universe's beginning and end. The Big Bang, in thermodynamic terms, may have been not a singular creation, but a fluctuation in a timeless equilibrium, a brief deviation within an eternal system. The expansion of the universe might be spacetime's way of redistributing its own heat content, spreading curvature across an ever larger domain to maintain thermal consistency. And the distant future, when galaxies drift apart and the stars burn out, may represent not decay, but completion, the return to perfect uniformity, where all geometry once again settles into its calm equilibrium. Seen this way, gravity's endurance is inevitable. It does not dissipate because it cannot. Dissipation would mean a flow of energy out of the system, but the system has no outside. The cosmos is self-contained, self-consistent, and self-thermalized. Gravity is the expression of that eternal balance. It is not a force in motion, but the steady heartbeat of equilibrium. This realization unites thermodynamics, quantum theory, and relativity in a single vision. It tells us that spacetime is not a cold void, but a living field of energy and information, perpetually in dynamic balance. It flexes and curves, but its total state remains constant. Every gravitational wave, every collapse, every expansion is a ripple within an equilibrium that never breaks. Thus, the dissipationless nature of gravity is not a mystery to be solved, but a reflection of the universe's perfection. Spacetime does not lose energy because it has already distributed its energy perfectly. It does not age because it is already timeless. It does not tire because it is already in rest. In the next step of this exploration, we turn to the quantum realm, where the vacuum itself, that strange, seething nothingness, reveals its own gravitational harmony. There, in the quantum view of the vacuum, we may find the final reason why gravity flows forever without loss. Because the ground state of the universe, the quantum vacuum itself, is a perfect conductor of geometry, carrying curvature as effortlessly as a superfluid carries motion. Beneath the smooth surface of spacetime lies a restless quantum sea. What appears to us as emptiness is, in truth, a storm of creation and annihilation, a ceaseless dance of virtual particles flickering into and out of existence. This quantum vacuum is not a void, but a living field, saturated with fluctuations of energy and information. Every cubic centimeter of empty space teems with activity so intense that, if counted classically, its energy density would surpass that of all the visible matter in the cosmos. Yet this ocean of motion appears silent. The universe does not tremble beneath its power. Somehow, gravity couples to it with perfect subtlety, neither consuming nor dissipating, as if the vacuum itself were an ideal medium, a perfect conductor through which gravity flows without loss. To see how profound this is, we must recall that in quantum field theory, all forces and particles emerge from fields permeating space. The electromagnetic field gives rise to photons, the quantum of light. The weak and strong forces manifest as exchanges of their own gauge bosons. Gravity, too, can be thought of as arising from a field, the gravitational field that describes the curvature of spacetime. But unlike the other forces, gravity's field is inseparable from geometry itself. It cannot exist against a backdrop. It is the backdrop. This makes its quantum description uniquely elusive. Physicists often imagine a hypothetical particle called the graviton, a quantum of the gravitational field. If such a particle exists, it would be massless, travel at the speed of light, and carry a spin of 2. It would interact so weakly with matter that trillions could pass through the Earth every second without leaving a trace. The very weakness of this interaction explains why gravity can remain coherent across cosmic distances. Gravitons, if they exist, would behave like perfect messengers, immune to the noise that disturbs all other fields. They would glide through the quantum vacuum as though it were frictionless, a pure medium that neither absorbs nor scatters their motion. But the reality may be deeper still. Perhaps the graviton is not a particle traveling through the vacuum, but a vibration of the vacuum, a pattern in the underlying quantum structure of space itself. In that view, space-time is not an empty arena, but a condensed state of some more fundamental field, a quantum condensate whose collective excitations appear to us as curvature. Just as sound waves travel through air or phonons through a crystal, gravitational waves may be the phonons of this cosmic condensate. And just as superfluids allow flow without resistance, the quantum vacuum might allow curvature to propagate without dissipation. This analogy is more than poetic. In laboratories on Earth, physicists have observed that certain quantum systems, such as Bose-Einstein condensates, exhibit properties that mimic space-time itself. Within them, sound waves can behave as though they are traveling through curved geometry, complete with horizons and analogues of black hole evaporation. In these systems, dissipation disappears when the system reaches its ground state. The particles move in perfect coherence and all motion becomes reversible. The same principle may apply to the universe at large. Gravity does not dissipate because space-time, in its quantum essence, is already at absolute coherence, its ground state perfectly ordered. The quantum vacuum thus acts as a perfect conductor of geometry. It carries curvature the way a superconductor carries current, freely, endlessly, and without resistance. In a superconductor, electrons pair up into coherent quantum states that move together as one, evading the collisions that normally cause electrical resistance. In the vacuum, perhaps the fundamental constituents of space-time, whatever they may be, behave similarly, forming a coherent whole that allows gravitational motion to pass through without loss. This picture also sheds light on the problem of vacuum energy. Quantum theory predicts that the vacuum should contain immense zero-point energy. Yet cosmological observation shows that the actual energy density of space, the cosmological constant, is astonishingly small. This mismatch, one of the deepest puzzles in physics, might arise because the vacuum's energy is not accessible to gravity in the usual sense. The perfect coherence of the vacuum cancels out its internal fluctuations, leaving only a faint residual curvature. Gravity does not dissipate in the vacuum because it has nothing to exchange energy with. The vacuum is already in a state of self-cancellation. Some physicists describe this idea in terms of renormalization. The vacuum's energy is infinite in theory, but the infinities cancel out when gravity's response is properly included. Others suspect that the cancellation is not mathematical, but physical, that the vacuum is a dynamic, self-stabilizing medium whose fluctuations balance each other exactly. Either way, the result is the same. The universe remains quiet, its geometry unruffled by the storm of quantum activity beneath. To imagine this balance, think of a violin string stretched perfectly taut. Even the smallest vibration can produce music, yet the string as a whole remains stable. The quantum vacuum is like that string, tuned to cosmic precision. Its fluctuations give rise to fields, forces, and particles, but the overall harmony remains unbroken. Gravity, instead of disrupting the music, is the geometry of the harmony itself. It does not consume the song, it is the song. In quantum field theory, particles appear and vanish in pairs, constantly borrowing energy from the vacuum and returning it in the blink of an eye. These fluctuations interact with all forces, yet gravity responds to their collective effect rather than their momentary bursts. It perceives only the average curvature of the vacuum, not its fleeting fluctuations. This averaging acts as a natural filter, preventing gravity from becoming turbulent. It ensures that space-time remains smooth on macroscopic scales, even as it seethes microscopically. The vacuum, in this sense, is not chaotic, but self-regulating. This self-regulation could explain why the universe's geometry remains so consistent across immense distances. If space-time were a fragile or dissipative medium, it would distort and crumble under the weight of quantum fluctuations. Instead, it maintains its coherence. Galaxies billions of light-years apart obey the same laws, as if connected by an invisible superfluid web. This coherence suggests that the quantum vacuum is not a random froth, but a deeply ordered state. one that binds the cosmos together in an unbroken network of information. The connection between gravity and quantum coherence also hints at a possible reconciliation between general relativity and quantum mechanics. For decades, these two pillars of physics have resisted unification because they describe reality in fundamentally different terms, one continuous and geometric, the other discrete and probabilistic. But if gravity is the large-scale expression of quantum coherence, then the apparent conflict may vanish. Space-time's smoothness would emerge naturally from the collective order of its quantum underpinnings. In this way, the dissipationless nature of gravity becomes the bridge between the classical and quantum worlds. There is another clue hidden in the holographic principle. The idea that the information content of a region of space is encoded not in its volume but on its boundary, much like a hologram stores a three-dimensional image on a two-dimensional surface. This principle, inspired by black hole thermodynamics, suggests that spacetime itself is a projection of deeper information. If so, then gravity is the manifestation of how that information arranges itself to maintain equilibrium. The vacuum is not empty, but informationally full, and its perfect coherence ensures that no information, and therefore no energy, is ever truly lost. In this light, the dissipationless flow of gravity is not merely a property of waves or fields, but of information itself. The quantum vacuum, as the ultimate information medium, cannot absorb gravitational energy because it is already in its lowest possible informational state. Any disturbance is instantly rebalanced, maintaining the total information content unchanged. The universe, as an information network, never forgets. Thus, the quantum view of gravity completes the picture that began with general relativity and thermodynamics. Gravity does not lose energy because space-time is not a passive stage, but an active, perfectly coherent field. The vacuum beneath it is a conductor of geometry, a medium so pure that motion through it encounters no resistance. It is both the foundation and the guardian of cosmic memory. Every gravitational wave that moves through the vacuum, every curvature that evolves, and every horizon that forms or evaporates is part of this grand coherence. The universe does not dissipate because it is already whole. Its structure is the equilibrium of quantum motion and geometry, the stillness beneath all change. And so we come to the edge of a new understanding. If the vacuum is the perfect conductor of gravity, then perhaps gravity itself is not an exchange of energy at all, but a flow of information within the universe's deepest layer. The next step in this journey leads us there, to the idea that gravity and information are one and the same, the geometry of knowing written into the structure of spacetime itself. If the vacuum is the perfect conductor of geometry, then gravity may be more than curvature. It may be the language through which information moves across the universe. Every vibration of spacetime, every orbit and wave, is a message written in the grammar of geometry. In this sense, gravity is not the pull between masses, but the flow of information through existence. In holographic and emergent gravity theories, spacetime itself arises from information. The positions and movements of particles are not independent entities, but consequences of how information arranges itself across the universe. The holographic principle tells us that the amount of information within any region of space is proportional to the area of its boundary, not its volume. This means that everything inside a region is encoded on its surface, just as the universe's history may be encoded on its cosmic horizon. Gravity is how that information rearranges to preserve consistency. Entropic gravity, a model proposed by Eric Verlinde, treats the force we perceive as gravity as an entropic effect. When two masses approach each other, the information content of spacetime between them changes. This change in entropy produces what appears to us as attraction. But this is not dissipation. It is equilibrium seeking. Gravity emerges not from energy flow, but from the universe's tendency to maximize information balance. If information is the foundation, then nothing is ever truly lost. Even when matter falls into a black hole, the information it carries is believed to remain encoded on the event horizon. As the black hole radiates, this information may re-emerge, hidden in the correlations of Hawking radiation. What once seemed to be the ultimate loss, the disappearance of matter into darkness, may instead be a perfect transformation. Gravity becomes the guarantor of cosmic memory. The dissipationless nature of gravity now takes on new meaning. It is not just that space-time has no friction, it is that information cannot vanish. The total informational content of the universe remains constant, merely redistributed through changing geometry. Where entropy increases in one place, order rises elsewhere to balance it. The universe evolves, but its total information remains eternal. In this view, the gravitational field is a network of communication. Particles, stars, and galaxies are nodes in an immense web, connected not by force, but by information exchange. The curvature we observe is the geometry of that communication, a record of how information flows through time. Every gravitational wave is a story told by matter to the cosmos, and space-time itself is the archive that never forgets. If the universe's structure is fundamentally informational, then energy, entropy, and geometry are simply different expressions of knowledge. Gravity, then, is the way that knowledge stays coherent. It does not decay because truth cannot disappear. It reshapes itself endlessly, ensuring that what was once known remains encoded in the structure of reality. Imagine space-time not as empty geometry, but as a vast quantum superfluid, a cosmic ocean whose currents form the structure of reality. In a superfluid, motion is frictionless. Whirlpools can spin forever, sound can travel without attenuation, and waves can cross without loss. Some physicists believe that space-time behaves the same way. Its curvature and flow may correspond to quantum vortices and ripples in this superfluid vacuum. This idea, explored by researchers such as Grigory Volovic and William Unruh, draws parallels between gravity and the collective behavior of condensed matter systems. Just as sound waves in superfluid helium mimic gravitational waves in space-time, curvature in the universe may represent organized motion in the underlying quantum fluid. If the vacuum truly behaves as a superfluid, then gravity's dissipationless nature is no longer mysterious. It is the natural consequence of superfluidity on a cosmic scale. In this model, black holes are vortices in the quantum vacuum, and their horizons mark regions where the flow becomes so extreme that nothing can escape. The event horizon's thermodynamics, its temperature and entropy, arise naturally from the superfluid's internal structure. The entire universe, in this view, is a self-sustaining flow of geometry, a sea that never runs dry. Such a picture merges relativity, quantum theory, and thermodynamics into one continuous story. It portrays gravity not as an external force, but as the motion of the quantum vacuum itself. The dissipationless quality of gravity is thus the ultimate sign that space-time is not a material substance, but a perfect quantum state, a fluid of reality whose flow defines existence. Gravity endures because it is not a traveler in the universe. It is the universe. Where other forces fade, gravity simply is. It does not burn fuel or release heat. It is the quiet rhythm of existence, the geometry through which all things move and remember. From Newton's pull to Einstein's curvature, from black hole thermodynamics to the quantum vacuum, we have followed gravity's trail through the deepest laws of nature. Each step revealed that gravity is less a force and more a pattern of equilibrium, a manifestation of perfect order that never loses energy because it is energy in its most balanced form. The dissipationless theory tells us that gravity does not need to fight decay because it exists beyond it. It is the self-consistent harmony of space-time, the dance of geometry that never grows old, the universe's expansion, the flow of information, the ripples of black holes, all emotions within this eternal balance. Perhaps this is why gravity feels timeless. It links the birth of the universe to its farthest future, shaping both equally. It does not age, it does not tire. It holds galaxies together for billions of years and carries the faint whisper of ancient waves across infinite distances, all without ever dimming. Gravity is not what moves through space-time. It is space-time. It is the melody of being, the dance that requires no energy, because it is the definition of energy itself. When all lights fade and the stars grow cold, gravity will still flow, silent and perfect, the final reminder that the universe endures through balance, not through struggle. Gravity does not burn, break, or tire. It is the rhythm of existence, a dissipationless dance of geometry and time. Where all other forces fade, gravity remains, because it is not what moves through the cosmos. It is the cosmos.